hear me well. From single smart plug towards AI-powered house, transitioning to open source intelligent home automation. Some stuff and some things about me. For those who don't know me, I started using Nix OSs in the early 90s, starting with SUSE Linux. Got in touch with FreeBSD around 2000 through our hosting provider from Bremen. And I've been migrating stuff to on FreeBSD for more than 10 years now. I've been contributing to ports for many years as well, like OpenSearch, SaltStack, and stuff. I really love to combine enterprise-grade solutions with fun projects at home. Sorry. Short overview, what to expect. Something about the motivation, why I did this project, some historical challenges, of course, the role of FreeBSD, some things about the hard and software platform, getting pseudo high availability on FreeBSD, creating machine learning models for comfort, environment, and fun, and, oh, sorry. Just as a disclaimer, everything is work in progress, so it's not completely finished yet, but it's evolving from week to week.
For your motivation?
Yeah, so I've got a boring day job, so I need to be, need challenges at home, let's say, yeah. So it all started with a fun project to play with home automation. When we found our house that needed full remodeling, that hobby turned into a real challenge to create a self-learning and energy-efficient smart house. So the goal was to reduce especially energy costs and CO2 footprint through the integration of photovoltaics and state-of-the-art heat pump. So, and for those who are not familiar with the environment, at least the energy prices in Europe right now, or in general, but especially in Europe, should concern everyone. And I haven't seen a single solar panel on a private house in Ireland coming in here. So, really, I haven't seen any coming from the coast. So there were solar farms, but not on private properties. So maybe they should think about this as well. Some historical overview and challenges. I started with home automation without real benefits, like just turning on a light on and off. And 8 years ago, I bought my first, or used the first Raspberry Pi with home automation. And those who are familiar with this, these are wireless solutions, Zigbee and Z-Wave. They work pretty well. This is actually the first single smart plug I used, and connecting it to the mesh was like, it had 4 buttons. You had to press 3 buttons, then release one, wait for 5 seconds, release the third one, then you needed another toe to push another button, and it was like, no. It took me half a day to get this running. Then Debian and systemd kicked in, so I had issues migrating scripts to systemd. I didn't want to learn systemd from ground up. So I tried the Home Assistant OS, HasOS. It's Docker-based, so you can imagine everything messed up. I tried to get Home Assistant running on FreeBSD, as I've been using it for databases and stuff, and was like, yeah, why shouldn't I run my home automation on FreeBSD? But the Python libraries didn't build at time. There was no ZFS support for Raspberry Pi at that time, so I totally failed. I continued. I went back to a Debian-based system, which is called Raspberry, a special build for Debian built for Raspberry Pi. But the maintenance was a pain in the bash. So as I needed more power, I went to an ARM64 CPU, and finally took the chance to finally move to FreeBSD. I started with a small HP-reliant microserver with a Celeron, I think 8 gigs of RAM, At that time, the Raspberry Pi only had 1 or 2 gigs, so it was major improvement for me. And a couple of years ago, we found our house that needed a full remodeling. So I took the chance to build everything from ground up, say, okay, take all the knowledge I get and try to build a new home automation, like, next step. So yeah, of course, I scaled up to multiple Dell pizza boxes, combining playgrounds and production. I'm maintaining the open search port, so I need my bootware and all that stuff, and then you need backups. So it quickly escalates once you start with your first 90-inch rack. So some facts about the hardware, the underlying hardware, so real hardware. So as I already told, wireless solutions never proved to be stable enough. They were like, if one device in the mesh is broken, the mesh has to be rebuilt, and if you're walking through the stairs and the lights won't turn up, it's not a great thing. So if you have no other chance, you can do this, but I decided to use a wired. It's called KNX. It's pretty standard in Europe. It's used for private and industrial buildings. It's a 30 volts bus system with central actors. So the logic all resides in the electrical cabinet. And I removed every single power switch in the house. So there's no physical power switches anymore. Brett asked me how this looks. This is actually these devices. They're sensors and switches as well. So you can push a button up, just single tap to turn on the light, single tap down to turn off the light, hold it to dim it up and down. Like in the kitchen, you double tap to bring it to full light and turning the shades up and down. Turn on the coffee maker, of course, and there's like humidity and temperature sensors. You can turn the temperature up and down in every room I have. They're fully programmable, so if I want, I could turn on my EV or turn the heating on in my EV with a button. They're programmable. And this is a motion sensor, so most of the house is motion triggered, so I don't need to touch all these things. So what did I need? It was more than 1.5 kilometers of power cables. Every room has 6 independent power lines. These are the 5 wired cables, 2 5-wired cables, so 3 phases. Should I move it a little bit? Here we go, perfect, thank you. So, great. Of course, you need Ethernet, so added 0.5 kilometer of Cat7 cables. There are 2 dual sockets in every room at least. So and KNX bus wires. These are for connecting all the switches and stuff. So later I added the photovoltaics, 14 kilowatt peaks and a 70 kilowatts battery, and with off-grid emergency power, which is really great if you're on a conference and everything turns down. So it had proven to be, it actually was at EuroBSDCon in Vienna, where my wife called, so everything's turned down and the switch didn't trigger to turn on the off-grid emergency power. Was not a nice thing at 1 in the morning. Yeah. Another thing is the IP-based heat pump, so which is actually required to optimize all the heating and stuff. So when we bought the house, I had 2 months to develop the system and find out how this KNX stuff works. So I bought some of these actors, like the power supply, the IP bridge, see the Ethernet cable, and just took a multimeter, turned on switches on and off and checked it with a multimeter. So you see you can switch up to, there's a 24 one, so 24 power lines in just this small device, which is really great. This is a light dimming actor. How it started was putting cables and cables and cables. And I decided not to put them behind the wall, so I just added another wall. There were so many cables. It's like, okay, I can't tear down everything. Just place them on the walls and added another wall in front of it, because you see it's there's a separate server room in the basement, so that's the electrical cabinet. So it's not in my living room. So my wife would have killed me. So yeah, once you add a single server rack, you're probably gonna add another one. See all these. It's what happens, and then you add the photovoltaics and a heat pump. Just for the record, I use 2 large water tanks because it's much cheaper to store energy in thermal energy. So I'm turning on the heat pump or optimizing the heat pump to most efficiently power up or power these water tanks for heating and no, don't spoil it. Okay, so many people will think, okay, he's got too much money and too much spare time and just wants to show off. It's not like that. Actually, the overall cost for all the electrical installations were about 20,000 euros. So, which is for remodeling a whole single home, that's pretty cheap. So the companies I asked for, they said, yeah, for a single room, it's about 10 to 20K to put the wires and some sockets. But yeah, there's something. So endless hours and work of family and friends, of course. I bought used servers, the pizza boxes, which were around 100 to 200 euros. So 5-year-old things. And calculated a photovoltaics with a return on invest of about 8 years or less than 8 years, and the heat pump around 10 years and without any optimization. So we're here for BSD. So what's the role of BSD? I mean, I actually don't have to tell you all this. For a stable and easy environment, ZFS and boot environments, enable very free upgrading. You all know this. I use jails, especially Bastille, for testing and updating. I'm going to show you some things about it later. And one fact for me was the tier 1 ARM support, for porting it to embedded systems. If you see half of the electrical cabinet over here, there's this small device. It's a Raspberry Pi, which has a connector for the electrical cabinet. So you could actually run not the current state of this project, but later maybe not getting rid of the 19-inch racks, but it would be possible to put it on ARM servers or small ARM devices to be much more power efficient. So the platform, there are 2 KNX IP routers, which translate the KNX protocol to IP. They use Dell pizza boxes, only 2 units. I use the low power CPUs, which are not really, which are really power efficient. Performance is not that good, but for home automation and learning and boot rare, it's really great, and the power consumption is way below the normal ones. Yeah, of course, FreeBSD, ZFS, boot environments, and jails. Except for the GPU server, we need to talk about this. There's no CUDA support for FreeBSD right now, which is really bugging me, but it's not part of this talk right now. Yeah, Home Assistant, many of you might be familiar with that. It's a great Python-based home automation system. I basically use it for data normalization. It's got a lot of plugins for all different kinds of APIs and stuff. And for visualization, so I've got cheap Android tablets in my home with the Home Assistant, so I can just switch everything I want, turn on lights, shutters. It's especially useful. There's the, what's it called? Got it. The any Siri interface, home. Who knows it? HomeKit, yeah, the HomeKit integration. So I can control everything with my watch or my iPhone, but I don't always have it on me, so there are still tablets to do all this. There's Apache Kafka for real-time triggers and as a message buffer, and OpenSearch as a long-term storage, as I need a lot of data to train this model. So why all this effort for home automation? So yeah, automatic lighting is quite comfy, but not really necessary. I mean, there's no real benefit except saying, okay, yeah, lights turn on and off automatically. Okay, I can do that without all this. The real deal is the energy optimization. There are quite some challenges, sorry, like multiple heterogeneous data sources, which require very complex machine learning models, the necessity for continuous and robust data. So missing information could really be a deal. There's one example. The heat pump only knows inverting the state from heating to cooling. So I don't know what the actual state is. So I once missed during an update the switch between heating and cooling. And then my sensors were like, oh yeah, I'm in heating mode. I don't need to turn on the valves. The temperature is already high enough, but I wanted to cool it down, so I needed to turn on the valves to get cool water into the system. So yeah, took me a couple of while to figure that out, why it didn't work. So yeah, as I told, data quality has a very high impact on the model accuracy. So the goal was to create a proof of concept for self-learning home automation. Of course, yeah, that's fine. So maybe not everybody needs 19-inch server racks at home in your basement or any cloud services where they reside on. So all components, as I already told, are ARM compatible, might be migrated into smaller devices. And only the training requires modern GPUs, which are quite expensive, consume a lot of energy, and yeah, therefore it's not suitable for every home, but I'm gonna catch that up later. So the setup. You've got information from persons moving around doing things like turning on washing machine and dishwasher, and you've got all the IoT sources, if it's REST APIs or the KNX parameters that are running all the time through the bus. Information from the heat pump and all the information you gather from the solar panels. So everything's aggregated in Home Assistant, which is basically used for normalization, and then published to Apache Kafka, as well as ingest to OpenSearch. The reason I'm using both in parallel is if there's any issues in OpenSearch, they need strict templating. So if a sensor or the API changes from binary to string or whatever into float, and I can easily reset the offset here and re-ingest all the data. So Apache Kafka is for real-time events, and as a message buffer for up to 6 months, and yeah, OpenSearch as the long-term storage, which has now data from 1.5 years. So, but it's probably going to be more as time goes by, of course. Yeah, you see, it's not very bright, this projector. Yeah, re-ingesting data is also a thing. But, so we've got external proprietary sources and all the FreeBSD-based stuff, which can be ported to like low-power SOCs. But there's an issue. It's too slow. Because Home Assistant does not offer any support for clusters. So As I told you, I need continuous data, and sometimes upgrades fail, take longer than expected. So I needed to find a way to get Home Assistant running at all the time. So I can't miss a second. Maybe that second I'm missing valuable information for the model. So I'm using jails with ZFS, send and receive to get a 0 downtime. Gonna show this a little bit graphically later. I create an A record with a low TTL for every jail. And when upgrading, I'm just simply moving the A record into another jail, so I can easily upgrade the primary system, then switch back the A record. The only issue here is make sure you're pulling data from that system the A record is on. I'm going to show it right away. So, and putting large databases or data outside the jail. So if you're moving data or the jail with ZFS send receive, you don't want to migrate like 20 terabytes of data. They can reside on the primary system. How does it look like? So I've got a primary host, so probably some more, but let's say that's the primary host where Home Assistant is on. It's got the IP.1. I'm moving this jail to a secondary host with ZFS send snapshot, and then send it over and give this one the IP.2. Bastille's really helpful at that point as the configuration, all the jail configuration is outside the root system, so it's easy, just move the root partition. You can do this on a single host as well if you're not intending to upgrade the primary host, the host itself. If you're just upgrading the jail, you can just do it on the same host, just clone the data set. But let's say I want to update the whole host. I'm sending it over to another host. Then I'm switching the A record. Let's say it's called Home Assistant.local, switching the A record to jail IP.2, and I can easily upgrade a primary jail and put the pointer back to the primary host with the IP, or the jail with the IP.1. So the issue here is Home Assistant also has Kafka connectors and I think OpenSearch, or at least Elasticsearch. But if you're using these connectors, they're going to push data. So if you have two systems running, you're going to get duplicates. So that's why I'm using my own Python scripts to gather data from the Home Assistant API, and it's just listening or looking for the A record, and once it's changed, it's going to gather data from this one. So 20 more minutes, perfect. RCD, everything. RC scripts. Mateusz, is he here? No. Mateusz did a great, so ZeroMP at FreeBSD.org. He did a very great talk about RC scripts, RC8, actually. Just covered it a little bit, but you definitely need to watch his talk. I think it's recorded. RC scripts are really easy to write. I'm using the Python module Watchdog for Python scripts. You see, it's just, I don't need more than this to get my RC scripts running. And of course, you have to make some mistakes in your slides. It's what it's called, as well as not ADSB. But anyway, that's everything you need to get your Python script running. That's the Home Assistant to OpenSearch connector I have to get it running constantly. So here's a slide. You need to remember the exact numbers here. You can read it. It's your problem, not mine. I'm going to point to that later. So you see the solar radiation here, which is very low on that day, these 2 days. And here the solar radiation is very high, so a sunny day. And you see the buffer temperature, water buffer temperature. As it's getting sunnier, water temperature rises. It's what I control. And this can be done with, without any machine learning models, just by using load management. But there's more than this, than just turning on the temperature. So getting to the nice buzzword, artificial intelligence. It's what everybody needs. Everybody needs artificial intelligence. Yay! So yeah, I'm going to do a talk. I thought it's great to have this in the title, so everybody will join. So actually, artificial intelligence is like a huge huge topic. We're talking about machine learning and especially about deep learning. So it's just a small part. And it's not only ChatGPT, which resides here. ChatGPT might be somewhere around here, but there's more to deep learning and neural networks than just ChatGPT. So this actually, I took this photo a week ago at home. So this is how my house looks. Yeah, that's me. That's me. Yeah, you see, I'm writing the RC script here. So yeah.
Is your wife there?
No, my wife's in the basement. So she's behind the walls here. I'm hiding her in the picture here. So, and that's not my wife here, no. So, let's get started. OpenSearch built-in anomaly detection. I choose a simple example. It's window sensors to show you how it works. To get to the end at first. If my windows are open for too long, I'm going to get a push notification via pushover. It's a great free API, pushover.com or .net. And it's going to tell me window in the sleeping room is open for too long. So how do I do this? This is the OpenSearch anomaly detection. And you see, this is the actual room temperature. So you see room temperature drops. It's about 19 degrees, and this one is about 12 degrees, so pretty cold for the sleeping room. This one, it uses random cut forests, which is basically, or can basically learn over time. It can do seasoning, so it's not, I can say, yeah, if the window's open for 5 minutes, just send me an alarm. In the winter, it might probably be good, or if it's very hot outside. During spring, maybe I can leave open the window for, or need to open it for like 2 hours to get fresh air in, circulate everything. So I'm using anomaly detection. And you see over here, this is the anomaly which is detected. And you see, oh, sorry. No, what the heck? Just leave it here. Don't touch anything. Here we go. Okay, you see it's expecting the temperature to go up at that point. So the window's open for too long, the temperature is decreasing too deep, and you see it takes a long time to recover to get to 19 degrees again, so I need to heat it up. If I had closed the window around here, I wouldn't have needed that much energy to heat it up again. So some more facts about machine learning. Outliers. For those who don't know them, they're like cockroaches. Nobody likes them, but they're there, and they reside in your data. So this is the energy consumed by the heat pump per day in kilowatt hours. So at that point, data tells me I consumed 35 megawatt hours a day, which is probably, I didn't do that, really, I swear. So it's probably some fault. It turned out that the API has an issue. I'm not sure if it's the API itself or the implementation, the library, but if you restart Home Assistant or the API or the heat pump, it's going to send the max value once. So you have to remove this, and then you see a nice distribution. So it means around here, around 5 kilowatt hours per day, which is really okay. And the maximum is 8, and sometimes when it's warmer, I only need 2. So cleaning up this data is really important, otherwise it's going to destroy your machine learning model. Training the model. I use a dedicated machine learning server for that. It runs at 300 watts, which adds up to 200 kilowatt hours around roughly per month. That's 100 euros just for energy for training the model. So I simply use it on demand. I integrated a small switch in Home Assistant, which can turn on the server via IDRAC, which is the IPMI from Dell, and turn it off via SSH command send -p. So I only the times I don't need to constantly train the model. I'm doing this sometimes a couple of days a month, sometimes every 2 months. So basically, if there's new information or new stuff I want to try out, so I'm only using it on demand. It's not what servers are meant to be, but you see, I don't want to spend the server $100 just for idling around. So this one's a Debian, as there's no CUDA support for FreeBSD right now, which is a big issue. There's initiatives from the FreeBSD Foundation and a couple of vendors to get this running, but it's a big issue. Maybe Beehive pass-through, if Beckhoff does a little bit more, Corvin K, maybe we can get this running on Beehive so I can replace the Debian machine with a FreeBSD. So I fetch all the data from OpenSearch, clean it up, you have to normalize it again, and then train and validate the model. There are issues with deep neural networks. Binary sensors never turn up to be 0 or 1, true or false. Everything is, it doesn't know any binary, and if you're training it over time, it will turn out to be, let's say, 0.999, but not on, not 100%. So you have to look at the thresholds to say, okay, 0.999 is probably a on, so a 1, and 0.01 is off, and 0.4, I don't know, just wait. Exactly. So yeah, that's it. So you have to look at the data very, very deeply. So as already told, calculating the model needs a lot of power. It needs or requires expensive GPUs. So my goal is in the future to build a more generic model that you can easily adopt, gather some information, some data, and then just reinforce the model, this generic model. So it needs a lot of memory. So I'm using, let's say, cheap NVMe drives. You can get 4 terabytes for about 100 euros on Black Friday. So it's much cheaper than actual memory. And as I'm only using it once to pull all the data and cache it for training, it won't destroy the NVMEs. So it's a pretty nice way to extend your memory. So everybody hates swap, but with an NVMe, it's quite fast. The biggest issue the biggest thing I did was predicting the self-sufficiency, which means, I want to know, I don't want to consume any energy from the grid. I want to be as self-sufficient as possible. So the goal is to get 100% self-sufficiency, and that's what I trained the model for. It's the first model I created. It's an autoencoder, which does not really fit. It's a little bit small. Blue is predicted values, the model predicted, and red is the actual one. So if you're looking over here, remember the numbers from the slide? The solar radiation. So these were 2 cloudy days. So there was not enough energy to store in the battery. So I only was able to get 100% self-sufficiency around here, around noon. But in the evening and at night, I had to consume it from the grid. And the predicted model says, okay, yeah, you're like, what is it, about 80% negative self-sufficient, and you're about 200, is it? Yeah, it's 200% self-sufficient. So was like generating money. So that model didn't actually fit. And if you're looking over here, it didn't catch the battery. So it says, okay, every 2 o'clock in the evening, definitely your self-sufficiency is going to decrease. And the next day, it's going to increase. So this model didn't fit at all. So I created a much more complex model. Here's the training and validation loss of this model, which says, which is down to 0.1, which means the predicted values actually fit the real values calculated. How does it look? If you look at over here, compared to the other one, you see the blue dots are the predicted values, and the red dots are the actual values. And it even caught the information about the battery. So saying, okay, probably this is a sunny day. Oh, I forgot to tell, I'm using multiple APIs, public APIs for the training. I'm at a weather break, so I'm using 2 closed weather stations, gathering information from different sources like Met&O and Weather Underground, and put it all together in a model, because weather predictions are getting, feels like worse. So they say it's going to be sunny tomorrow, and then it turns out to be rainy all day. So I'm taking multiple sources into the model and getting a really good prediction. It also, why I'm not using this, things like, it's called Solar Forecast API, which can predict the energy usage, but it doesn't know how I'm acting in my home when I'm usually turning on the dishwasher, what all the devices in the house use, from servers to whatsoever. So I'm putting in all this data and then get a really high efficient model. So you see it over here. Yes, still some things to do. One thing is I hope I'm finished now. Not all APIs are well documented. So sometimes it turns out there's a new value, and everything has to be numeric. So machine learning does not know what sunny is. Even if you're using LLMs, they all turn out or will be converted to vectors. So I'm doing this manually, and I'm saying sunny is like a 10, cloudy is a 5, and at night it's a 0. And then it turns out they say it's half partially cloudy, a new value, and then I have to put it in again. So I hope I caught all the crazy names they found for the weather. Yeah, next thing will be reinforcing the model with a sliding window on Kafka. So constantly involving or reinforcing the model with new information. Right now I'm just doing that in batches every couple of weeks. Level 2 would be automatic cleanup, which turns out to be much harder than expected. For the heat pump, it's probably easy. You can use quantiles to figure out what information is too high or is out of range. And level 50 would be creating a generic model where you can port it just to every electric cabinet. Just take your small Raspberry, hang it in, plug it in, and that's it. So I think that's pretty far away from this. So yeah, another thing would be enabling to constantly evolve it without any interactions. So automatically reinforcing the model. So, and there are even more issues. Bought an EV 2 months ago, or leased an EV, which consumes about 40% of the electrical power. So totally destroyed this model. So this really, I'm gonna fix it. So no, because it doesn't know when to charge. I'm disconnecting it. So that's the biggest issue. So maybe I'm charging it once a week, maybe every day, connecting it so it doesn't know. It needs to learn my behavior of charging. So I can fix that, but right now the model is broken. So missing deep learning support for FreeBSD is another issue, I'm already told. I tried to fix it for OpenSearch. The anomaly detection is working, but other stuff, the ML library, isn't working, and they replaced it a couple of months ago to a new Java-based, new Java library, which is really complex. So you need to port it to FreeBSD. Yeah, you're missing CUDA support or neural network support, and no Google Coral TPU. For those who don't know these, TPUs are really small. It's called tensor processing unit. Small devices or small chips, which are optimized for running TensorFlow. So, as a conclusion of all this, yes, FreeBSD offers a stable environment. Everybody knows it. It's really energy efficient. So if you're putting it on a SOC, it doesn't consume 800 megabytes of RAM right away. You need stable data sources and storage. That's why the DNS solution for jails. Yeah, and one thing, you should add some extra backup, like battery-powered SOCs, for like smoke detectors or security devices. You don't want them to rely on any machine learning model, so always have a little backup to control this. So, as you see, this model can look into the future. It's like this. Okay, just 2 minutes left. Sorry.
Hi. So I was wondering how much data are the logs and all of the OpenSearch data using?
It's about 5 terabytes, only sensor information. So depending on what's going on, sometimes it's about 10 to 20,000 messages a minute. So there are questions why I'm not using MQTT and not using OpenTSDB or InfluxDB. The reason I'm using Kafka is for scalability. You could port it to like huge environments, business buildings, business complex. And the reason for using OpenSearch is I don't want to use a second system. There's built-in machine learning. I can recalculate data, I can transform data, aggregate it, whatsoever. That's why I'm using OpenSearch instead of a time series database, would be more suitable for this, but I'm doing more stuff with it. So, yeah. That's a very good point. Yep.
For a colleague who runs a full one-family house with home assistant, we use the JOS VM, which is also like this.
Fun fact, I use it in a jail for quite a while. I switched to a Beehive for a month or two. You can use it like the thing I told with jails, you can do it with Beehive as well. Right now, the issue is that Python 3.12 is not ported to FreeBSD yet. The port's not finished. And I'm using a mixed like built-in features, like grabbing the libraries automatically via Home Assistant and using ports as well. So I need to combine it. So it takes some time. I cannot upgrade it every week. So I'm upgrading it like every 2 months. which is quite okay. I'm only if I need a new library and stuff or security issues. So it's a pain in the ass, yeah, definitely.
Can we continue with questions for a few more minutes?
Yeah, if you're fine with it.
I'm just curious how you were measuring consumption. Like you said, your heat pump used 5 kilowatt hours a day or something like that.
Oh, it's integrated in the heat pump. The heat pump itself knows how much energy it uses, and all the electrical wiring measures the energy consumption as well. So these sensors, these actors, or they are called, measure how much energy is running on the single line. So nearly, not every device, but 6 power lines per room, you can really separate your devices and say, okay, this is for TV and stuff, and I know when the TV is turned on and off, and physically turn it on.
The device level or something like do you use like circuit transformers can work quite well.
I'm not using any Shelly device whatsoever. It's integrated in this,
Each device.
each power line. Where was it? Each circuit, yeah. Let me find it. So every power line is measured on this device as well. So these sensors, I can use it for switching, for turning it on and off, and it measures also the energy running through this power line through this circuit. Yeah. Yes, it's in the model as well. I've got a simple switch which says I'm at home, out of the house, which means I'm coming back soon, and on vacation, so vacation mode. So the model knows, okay, vacation mode, I don't need any energy, don't need that much energy. So it's going to turn the heat pump into echo mode, which is done manually. It's just a template playbook.
What are the action actually the system does for you? So, for example, it can turn off lights automatically, I imagine, and it warns you where there are unexpected consumption, I think. Since you don't mention motors, so I think it doesn't close windows.
Okay. So that's actually how the tablets look. You can see, okay, battery is full. Actually, power consumption is 3.3 kilowatts. Photovoltaics, turn it up. And this is the information. That's all the information for the heat pump. So I'm using parameters like heating curve rise, which means the heat pump uses more energy and larger can go up to 3, which means warm it up really fast. In the winter, on cloudy days, it's going to turn down to 0.5, which means only low energy, just try to heat it up a little bit. I'm setting target temperatures. Right now it's pretty sunny and I've got a lot of energy, so water temperature, the buffers are turned on to or set to 60 degrees. Might see the target here, just turned on, and usually it's 51 only. Now it's sunny and it turns the target temperature of the water buffer to.
So the aging is automatic, let's say.
Yes, yeah. So it's done with the, I'm sorry, do we have time? Okay. Yeah, I'm fine with it. So if you are, those who want to leave and catch some eating. So you see the actual temperature and the target temperature in the room thermostats. So every room knows what temperature, what's the expected temperature and the temperature, the target temperature and the current temperature. And then the heat pump knows it's all accurate. There's much more to this. I could do a week talk on that. But yeah, basically it's calculated how much energy I use, how much pipes are in there, and then adds it all up and say, okay, I need that much power with this heating curve. So,
Then I can ask you another thing if you over here. I can speak loud, no problem. Okay, you mentioned that you did all the cabling because you have trouble with the radio system.
yeah.
Did you try Wi-Fi or LoRa or what else?
Zigbee and Z-Wave, they were both having their problems. And I mean, if you're looking at, I'm not quite sure, it's 250 devices. So I would need a lot of batteries and switching, like getting someone, maybe getting another child just for switching the batteries every day. So replacing them. So there are motion sensors, door sensors, temperature sensors, electrical switches, shutters, shades. Yeah.
How about warm water? Do you have a separate boiler for that, or is that heated with the
It's both heated with a heat pump. That's why I have 2 water tanks. So one's for heating and one's for warm water, because you need to separate it for not getting any bacteria from the heating system to your drinking water.
So a non-technical question. Sometime in the far future, you might look to sell your premises. How will the new owner, how will you train the new owner?
No, I might publish it, some information about that. I'm an open source guy, so I don't want to make any money out of it.
How many defensive remedies do you still have?
I mean, I'm the only one who's got power in the whole city during a power outage. There were people standing, I forgot to turn out, it's now, I created a small automation for that. The power runs out and your outside lighting is still on and it's gonna glow in night. You can't imagine how it looks. For a whole city, there's only one house light up, like watching Netflix via Starlink, and okay, so probably you can make a lot of friends with that.
I forget what the actual situation was, but you said you were using swap for some reason.
Yeah.
And I was wondering why you didn't use a regular file system, a regular file, and then mmap that file into memory instead of using swap. I think you might have a lot more control.
Maybe I'm not getting it correctly, but I need a fast storage for training the model. So it constantly is gathering the data. It's pandas, for those who are familiar with Python. So it needs to be in memory. It uses this as in memory, and storing it on a disk will really slow down the process. So.
We'll talk later.
Okay, yeah, definitely.
Davis, and he's going to talk to us about address space reservations, rethinking address space management, pointer programming. Please.
All right. Yeah, so the, most of these words are probably familiar, but pointer provenance might not be completely familiar to everyone, and it's an important concept to the talk. So I'm going to go ahead and give a couple definitions of what it is. So this is part of the C standard, but as a response to a defect report. It says, implementations are permitted to track the origins of a bit pattern and treat those representations in an treat those representing an indeterminate value as distinct from those representing a determined value. They may also, most importantly here, they may also treat pointers based on different origins as distinct, even if they are bitwise identical. So an example of this in C is that you have two variables that are located next to each other, and two arrays, say, located next to each other in memory, and you do the thing you're allowed to do in C, and you get to the one past the end, and that overlaps with the next one. The compiler is allowed to know that those are different, even that the beginning of one array and the end of the other is different. A perhaps more succinct summary from the Rust community is just because two pointers point to the same address does not mean they are equal and can be used interchangeably. So why does this matter? Well, because pointer provenance is part of most of systems programming languages. So C, here it is in the defect report, and I cite a paper that you can look at online, which is long and complicated and full of horrible details and things you might rather not think about, but it spells it out. It is not yet part of the standard, but some form of it will be eventually. C++ also inherits this concept from C, and optimizers take advantage of it there as well. And then Rust. Rust recently adopted the notion that pointers do have provenance. But where I came to this from is in context of Cherry capabilities. In Cherry, we have capabilities which are bounded. So you can have one that points, whose current address is different from, is the same as some other capabilities, but only one of them, or maybe none of them, are allowed to access that data because they have different bounds. And that's enforced by hardware. So let's talk a little bit about Cherry. So in Cherry, we add a new hardware data type, the capability. We extend the instruction set to use capabilities, and we run all memory accesses through them. So what's in a capability? Well, capabilities extend integer memory addresses to add an upper and lower bound, as well as permissions and some other bits that I'm not going to talk about here, but were used for domain transition and a bunch of clever exploit mitigation techniques. And then capabilities are protected in memory by a tag, which says, and in registers, that says, is this capability valid? A capability that's valid can be used by a CPU instruction, and a capability that's invalid will not be able to authorize any access, whether that's loading or storing from memory or jumping to an address. When manipulating a capability, if you use a capability-aware instruction, so for instance, a set bounds instruction to shrink an allocation, if you do that in a way that's valid, the tag is preserved. If you do that in a way that's not valid, the tag is lost. Likewise, if you use a non-capability instruction, so for instance, a plain add to a capability to register, the tag is also lost because you didn't use a capability increment instruction. This prevents, for instance, overwriting memory that contains capabilities with different addresses and being able to load those and access the wrong thing. And on a Cherry system, all accesses to memory are via a capability. That's either explicit via new capability-aware instructions or implicit via default capability. So we have a default data capability and a program counter capability. So what do capabilities give you? Well, they have the integrity protection I've talked about, with guarded manipulation and requiring correct instructions. This ensures that you can't manufacture pointers out of nothing. and you can't just make things up and access the wrong thing. Similarly, bounds prevent you, of course, from accessing things that are out of bounds, so you can't turn a capability to one thing into a capability to another, to some other unrelated area. And monotonicity says that you can't take a capability that's small and make it bigger. To access, for instance, in this example, take a reference to something on the stack and turn it into access to the stack. I'd rather take questions at the end, I think. And then permissions allow you to decide what a capability can do. So you can have a read-execute capability, or you can have a read-write capability. In our current 64-bit implementations, you can have a read-write-execute capability, and in fact, it's pretty necessary for POSIX. But on some other smaller implementations, that's actually not even representable. You must have an executable capability or a writable capability. And so with these primitives, we get strong spatial safety with just a little bit of help from the compiler and the language runtime to set appropriate bounds. So we get your usual sort of view of memory safety, and we also can implement strong temporal safety for heap allocations. Because we can identify every pointer in the address space using a tag, we can in fact sweep the address space periodically, and I'll talk about that more later, to remove capabilities that should no longer be available. And then on top of all that, we can build scalable software compartmentalization. So we have a prototype that I demonstrated at the Dev Summit, so you could see it online, where we have each library is in its own compartment, and we're performing on the order of 1 million compartment transitions per second, which is completely inconceivable with process-based compartmentalization. So now let's take a little detour into one of my favorite XKCD visualizations. This is a map of the internet, almost 20 years old now, so someone should redo it. It uses a visualization called Hilbert curves, which take something that's linear and use this fractal to make compact representations of things that are nearby in a two-dimensional space. And in fact, this visualization and the desire to use it in this talk is part of why I wrote the talk, because I think I like the visualization and been trying to think about how to explain the ideas that we have in Cherry, and I thought this visualization would be cool and helpful, so hopefully it is. Now, before we get too far along and start talking about mmap in more detail, which is most of the focus of the talk, I'm going to show you a picture of a layout of a process. As I say here, it's not to scale. There's no address space layout randomization, because nothing makes any sense once you randomize everything. So we'll just not do that. So the first part of the process is on most ABIs, at the bottom of the address space, there's the page that would hold the null pointer, and it is not mapped, and you're not allowed to map it. And that is because there was a really nasty bug quite some time ago in Linux where you could trick the kernel into dereferencing the null pointer and executing it. And if in user space you had mapped a page there, then it would run whatever you put there. So that was bad. So we've made it so you can't do that unless you set a flag and you're running some ancient binary that for some reason requires it. So that's the bottom of the address space. And now let's put a program in there. So there's the text. That's where your code lives. There's data. This is predefined data that's initialized in the process. And then there's BSS, which is all the stuff that starts as 0 and you get to change it. It's all the global variables, all the static variables. Then there's what we call the break in conventional Unix. This is the end of your heap, and it's one of the ways you historically would allocate memory is you would increase the break, which is you would basically tell the kernel that I need some more pages after the end of my program. And the sbreak system call or the break system call is how you would adjust that. So you can move that up. You could nominally move your break up and down, and you would adjust your heap. In Cherry, we don't do that because the sbreak system call does too many things and has too many completely different meanings, and I just decided we could not square them with any kind of security, so it's gone. We took an even more aggressive approach than Apple did with a pure user space implementation, and we just deleted it. And the Emacs people said we were crazy. They were probably right, but they stopped using it, so it's all good. So that is the last I will talk about SBreak because it's terrible and you shouldn't use it. Now, at the very end of the address space, which in this particular iteration of the curve I've got down here at the bottom, there's in FreeBSD, there's the VDSO that we map above the stack. This is a shared data page. It's got your signal trampoline in it, your signal trampoline code. It's got access to time counters, so you can do get time of day. It's got your PID, all that good stuff. Then there is the stack up at the top of the address space. And then in FreeBSD, that's mostly actually what we call map guard pages. These are, they're not even pages, they're map guard entries. You can map over them with mmap fixed and say, I want to put a page there. And in this case, the kernel will automatically do so as you try to access them. But the entries are there so that you don't accidentally allocate that space to some other purpose. There was some vulnerability that caused this all to be created. It's all good stuff. And then there's what we more conventionally think of as a guard page at the very bottom of the stack, which is an entry with no permissions. So if you walk onto it and you hit it, you get a fault and you crash rather than starting to copy over some other thread stack or blowing up your program. And then at the top of the nominal heap is where the mmap system call starts allocating things by default. So at a program startup, after it's gotten to the beginning of main, you'll have done a little bit of allocation for thread local storage and the like, and JMalloc will have allocated some space. So whatever your malloc implementation will have done that. So let's talk about mmap. I'll give you a quick overview of the arguments, and then we'll go from there. So first, the first argument is an address argument. This is often called a hint, and the code and the documentation can't decide which one it is. That's in part because it actually is both. It says, in some cases it is, I want to put something here, and in other cases it's, I'd like you to put something around here, or actually I don't care, but you could put it here if that seems like what you want to do. Then there's the length. How large an allocation? How many pages do you want to map? The protections, flags, which say sort of how to map this. Is it if you're mapping a file, are you going to write back to the file, or do you just want to be able to read the data and then have a private copy? Do you want to map a file or not map a file? Do an anonymous mapping? There's a whole bunch of flags. Then there is a file descriptor and an offset. This is if you're mapping a file, that is what file are you mapping, and do you want to start at the beginning or do you want to start later? We're going to focus on the first four and not talk about the other two, because in this case we're mostly not going to talk about mapping files. So mmap does a lot of things, or gets used for a lot of things, I think might be more accurate. So it allocates space for malloc. In some allocators, you allocate from SBreak for small things, and for large things, you mmap. In CherryBSD, since we've killed SBreak, or on ARM, since we've killed SBreak, ARM64, everything's allocated by mmap. You can also map files. So in this case, if you wanted to open up a file and edit it in place, you can map it shared, and you can do that. You could also map a shared library. And the way mapping a shared library is typically done is you do one big allocation, whether that's something with no permissions, or in FreeBSD these days, we make a guard mapping, which is basically the same but different spelling. And then we fill in some bits relative to that reservation of space. So straightforward. But maybe you can do too many things with mmap. So here's something that does get used. You could make an allocation, and you can make another allocation, and then if you don't have a notion of pointer provenance, you might just decide to treat them as the same thing. So this is something JMalloc does. It's reasonably clever, it's not a terrible idea, but it doesn't work with Cherry because we can't combine, we don't provide a primitive to combine capabilities into another one. So we can't do that there. There's also, you can do absurd things with mmap. So why would you want to do this that I'm doing where I'm shingling these mappings? I can't think of any reason why you would want to, but it is something you can do because mmap just doesn't care by default. You can also do random mappings, and those, these are fine. Maybe this one's not so good. If you go and splatted allocation over your malloc implementation, that's
useful when you want to have a fixed memory layout and then you want to map a bunch of files into a fixed set of addresses you reserved earlier.
yes, but not that way. If you map them over your malloc, you get what you deserve. So now, the problems with mmap, as I see it. First and foremost, mmap conflates two different things. One, it allocates address space. So it says, I want some part of the program address space for some purpose. And usually you don't even care what part it is. You want some. Or maybe sometimes you say, I want this specific part of the address space for some purpose. And then it configures whatever you've put in that address space. And in fact, when you make an initial call, you do both. And that's just what it is, and that's the only interface we have to do this. Additionally, anyone who's calling mmap, any bit of code that's calling mmap can do anything that mmap can do. There are some things like map guard and the map exclusive flag, both of which are non-standard, which can prevent some errors. But every call is still with ambient authority and can do anything to the whole address space. And then worse yet, as I said, both of those are non-standard. MapGuard is definitely FreeBSD specific. Map exclusive, I can't remember if the other BSD is implemented. I think it is from 4.4 or 4.3. But Linux has some different spelling. They have some map fixed, no replace, I think is the name of the flag. It's a bit unfortunate we have divergence there. Probably we should agree on something and standardize it in POSIX, because the lack of agreement for anything but the most basic features makes it really hard to write portable code that does anything interesting. So let's talk about updating mmap for Cherry ABI. So first off, what is Cherry ABI? Cherry ABI is a new process ABI where all pointers are Cherry capabilities. It's implemented in CherryBSD, our fork of FreeBSD, and we're hoping to bring at least spatial safety to FreeBSD in FreeBSD 16, pending time and funding and hardware. But that's our current thought. So in Cherry ABI, the kernel provides bounded pointers for all mappings, or bounded capabilities. There's no way to get to a piece of address space unless the kernel is explicitly given you a capability. That includes the initial executable mapping, the mapping for the runtime linker, your stack, and anything that mmap returns. So it's all a matter of what capabilities you hold that controls what part of the address space you can access. Additionally, system calls don't violate those bounds. So you can't just make up a capability and then use read to go splat all over some memory. You have to have a valid capability to do that. And we make sure that the kernel uses those capabilities directly in all but, I think, 3 cases where we've been too clever in the kernel. And use it, copy in, copy out, use the capabilities directly. So if the bounds are wrong, doesn't matter, you can't confuse the kernel. It just goes, it'll hit the bounds. So in our code, mmap can only manipulate the backing of a mapping as part of the initial address space allocation or via an existing capability to that address space. And in fact, that capability must have a special software permission, the software VM map permission, to be able to change a mapping. And the reason for that is that we don't want people to be able to change the contents of pages that were given to part of them or all of them were given to them by malloc. If you have malloc, malloc controls that address space, and it's up to malloc to do the right things. So the capabilities that are passed out by malloc do not have software mmap do not have this software permission. This decouples, to the extent possible given the API, address space reservation and backing store configuration. Some of you may recall that quite a number of years ago, definitely pre-pandemic, I proposed an alternate interface, CM map, that would completely decouple these concerns. But since then, I think I've concluded that I can make mmap work well enough. I think there's still some good ideas there, but we can make mmap do what we need to do. So with the Cherry mmap, normal uses of mmap are unchanged. We don't actually have to, for Cherry, change mmap uses. We don't even have to, mostly don't even have to audit them. I'll get to one example in a bit where we do, but for the most part, everything just works because this is how programmers think about things. You know, we can map some space for a malloc, we can map a file, we can stick things, we can fill out a reservation for a shared library. It all is kind of how you expect. So you might have noticed back when I had a slide up of the capability that we have a 64-bit pointer, and then we have 64 bits of metadata, and somehow we have bounds in there, and that's 192 bits of data. So how do we make that work? Well, we compress the bounds relative to the address. And that means that as we get to larger and larger sizes, we have less precision in our length, and we have stronger alignment requirements. Now, this has some effects in malloc and in the mmap code. So sort of to illustrate this, let's consider some examples. So here's a messy, unaligned group of 14 pages. You know, it's kind of weird and ugly. We could align it a bit more if we moved it around. We could make it more compact. We could make it compact and strongly aligned. And in some cases, we might need to pad it. Now, if it were actually 14 pages in Cherry, we wouldn't need to pad it. We have considerably more bits than that. We have in both of the sort of application level architectures we have with RISC-V and with Morello, we have enough bits that we can precisely represent any object that fits in a page at any size and any alignment. And then as you get bigger and bigger, you will eventually get to the point that if you make a really really odd length thing that's long enough, you will have to start to pad it. But you won't have to do it at 14 pages. But this, I think, shows the idea at least. So I'll give you another problem we have, and then I'll talk about reservations and how we're solving these problems. So just like mmap, unmap can unmap anywhere by default. You can just go around punching holes in your address space. This is even a little bit true with Cherry ABI. If you have a capability with the right permission to an allocation, you can unmap parts of it, and there's reasons why you might want to do that. But that could be a problem. So let's say we have this allocation, we've punched some holes in it, and then some other mmaps came along and filled those holes in, which is definitely a thing that could happen. But now we have aliases between multiple mappings, and everything is sad, and undefined behavior is everywhere. We don't want that to happen. So how do we fix that? Well, reservations to the rescue. With a VM map reservation, which is a change we made to the VM infrastructure, the initial mapping creates the initial mapping in the address space that allocates some address space, whether a fixed mapping or not, creates what we call a reservation. And it populates it because that's how mmap works. If you create another one that happens to land next to it, those don't get merged because there's a capability to each one, and they're each in the VM system identified by the first address of the reservation. And so we don't merge them. So that does slightly increase VM fragmentation. However, it solves some problems for us. So when you start unmapping things, they transition to a state we call unmapped. And that is just like guard, but it has to be a separate state so we can tell the difference. Then, also likewise, when we pad, any padding starts in the unmapped state. So it's there and you can't touch it. We may want to change that eventually. I think we have some desire to implement mremap and allow extension in certain cases, but doing so is a bit fraught, and so we've not quite done it yet. No. And then a reservation remains around until all the entries inside it have transitioned to the unmapped state. Once that happens, we remove it. So now, let's consider another problem. Consider if you've mmap a file into memory somewhere, you do some stuff on it, you unmap it because you're done, and then malloc causes calls into mmap to get some more space, and it gets something that overlaps with the file that you had. And maybe you've left a pointer around and you use it by accident now. Now you have aliasing between the file and something that you've malloced, and that's going to be bad. So the usual answer, of course, in C, as it always is don't do that. Don't make that mistake. This is a sad and unsatisfying answer. So with Cherry, we can do capability revocation to solve that. This paper that I have a picture of on the right mostly talks about our user space, about the user space aspects of revocation. In user space, we maintain a bitmap shared with the kernel of all the capability-sized bits of memory that are allocated, and we can mark the ones that we're done with. So when we free them, we put them in a quarantine pool, and we mark them, and then we periodically call into the kernel and say, revoke all of this, revoke all the capabilities to the things that have been marked. And we scan all of memory. This is expensive but easily amortized, and overall, the overheads are really pretty reasonable in the paper. One of the things that I sort of slipped into the back of the paper was that we also do that for munmap. So how does this work? So a reservation gets unmapped over time. You start filling it out, and eventually it's all unmapped. Now, rather than removing the reservation at that point, we put it into a quarantine state. It hangs around in quarantine until it's eventually picked. So one other thing we do for optimization purposes is we take we allow them to combine. So if a neighboring reservation also goes into quarantine, they can be merged. And that decreases fragmentation in the case that we're doing a lot of mapping and unmapping. And then finally, the revocation path, when we trigger a revocation pass, if there are any things in the munmap quarantine, we'll go grab the largest, we'll walk the VM space, grab the largest one, and then we'll scan for it along with all these bitmapped, mallocked, or freed pointers. And then when we're all done, poof, we dissolve the reservation, and now the address space is available for reallocation again. So one other change we've had to make to mmap is something that's actually already upstream in FreeBSD, and it's, I think, a potentially useful, very minor mitigation. It's a propmax macro that allows us to specify the maximum protection the maximum page protection allowed on a given mapping. So if you set a maximum protection of, for instance, read-write, you can't later go in and mprotect that, use the mprotect system call to make that executable. So it's a kind of a handy trick. With CherryBSD, mmap, of course, returns capabilities, as I've said, and the property of monotonicity means that the capability you return from mmap needs to have all the permissions that you might ever want for that mapping. The problem we have is that it's a common pattern to use a prot none mapping, which we do with mapguard, to make an initial reservation and then fill things in. So we use it for libraries, for shared libraries, for instance. So we needed to fix that. So our solution was we created this prop map max macro, and we OR that with the regular protections to give an explicit maximum permission. So you can say, okay, I want to map this, and I want the mapping to have prop none, so no read, no write, no execute. You can't do anything with these pages until we change them. But I would like to be able to reserve the right to make them say read write later. And that sets both the maximum page permission in the VM entry, and that part is already upstream in FreeBSD. And we also use that to tell us what permissions to put on the capability that we get back. So therefore, for instance, with malloc, we set a prop max of read write because we don't feel that you should be using malloc for your executable capabilities. I will say there is another alternative here. The ARM Morello prototype just returns read write execute capabilities, and it's the responsibility of user space to decide to reduce those if they want to. It's simpler, and they didn't have the concept of a maximum page permission in their VM entries or the equivalent of VM entries, so they chose to do that. Yeah.
Can you specify that you want write and execute to be mutually exclusive with prop max?
No. Oh, so the question was, is it possible to use prop max to specify readx or execute? And no. It was intended to be as straightforward as possible. In Cherry ABI, I believe we currently enable WXRX by default at the page level. There's no sensible way to there's no obvious sensible way to do it at the capability level. We've talked about some possible ideas where maybe you have the ability to convert certain read-write capabilities into read-execute capabilities by handing one to the kernel. You could make it work. You could even make it safe using revocation, because you could destroy them all before you return, but it would be difficult.
But it does support double nmap ring buffers, right? So
What?
using that guard to create a double-sized reservation with read write, then mapping the same page twice.
You could probably do that, yeah. If you hate provenance and you're not using a compiler. So let's see, a summary of the changes that we've made for Cherry with regard to mmap. So the initial allocation of address space reserves a fixed amount of address space. There's currently no growth without simply reallocating. Next, there's no immediate, because of the temporal safety implications, there's no immediate reuse of unmapped address space. So you can't do mmap something, munmap it, and then map fixed in the same spot. You can't count on that working, and in fact, it doesn't work on all architectures. So that's generally an unsafe pattern, because you can't really know in a general purpose system if your program is multi-threaded. In fact, your single-threaded program might become multi-threaded by the simple virtue of, for instance, your system administrator configuring an SSLDAP and calling get PW name or something. So basically there's no way to know in the general case. So it's an unsafe pattern, and you just shouldn't do it. Where you need to do this, we've actually written some code in our test suite where we do need to say, okay, I need some definitely unmapped space, and the way we do it in our test program is we use libprocstack to actually walk the current allocations and find somewhere that's not allocated. So it's straightforward enough. It's also unsafe, but at least rather than the old trick of unmapping. So, and then you have to use prop max sometimes to control capability permissions. That's pretty much all you have to do for Cherry. But there are a few incompatibilities. So let's go back to that slide of weird things you can do with mmap. So this one's not so weird, but you can't basically grow an allocation into a single in place by doing this allocation. Or by putting something adjacent to it and then just treating them as one. It doesn't work in Cherry because of the hardware enforced provenance. So that one's not so bad. Also, the absurd things break in absurd ways, but you shouldn't be doing this. Likewise, the random mappings, they work here. We do support map fixed, even though it's not a very good idea. But if you try to map something right over the top of some other allocation, we don't let you do that. So, as a side effect of revocation, as I mentioned, address space isn't reusable immediately. So, stale capabilities will become invalid at some arbitrary point after an M on map, because it waits. Basically, we don't trigger revocation to get rid of them. In fact, we don't even have a direct way to do it right now to cause a specific one to be revoked. What we do have the ability, and so typically revocation will be driven by malloc deciding that there's too much stuff in quarantine. But we want mmap to behave consistently despite this. So we've set some rules, which I think some people find counterintuitive, but I think they're the best we can do. So if an address is a valid capability, then it must correspond to an active reservation, and you must be using map fixed. If you pass it for some other reason, just no. You can't pass it as a hint. Additionally, if the address is null derived, which is to say that it has no metadata and has no tag, it must not correspond to any valid reservation, because otherwise you could change the contents of anything and the whole software permission wouldn't work. By implication, we require that the address must not have any metadata. That address must be metadata and must not have any metadata and must be invalid if we're going to use it for map fixed to an empty space, because we don't want that to only work basically if you won the race with the revocation framework, because that would be really hard to debug. So we break something that could be sort of safe-ish, like you're not violating any key property, except that it's potentially really confusing and hard to debug. So I would rather be totally consistent. And if you want to do a map fixed at a location that you know has been freed up, then you should just cast the integer to void star, and you'll be fine. And it won't have any metadata and won't have a tag. So generally speaking, I recommend that you stop using map fixed unless any non-zero hint, unless you're acting within a reservation. The one place we do that in the kernel or we do that on the runtime right now is allocating thread stacks, because we want them to be at the top because it's easier to understand your program. What I kind of want is like a map search down to accomplish the same thing without any hints. I think that would be helpful. So there are some incompatibilities here. And of course, the question is, do they matter? Well, it gives me an opportunity to show one of my other favorite XKCDs, the infamous spacebar heating example. You're always at risk of breaking someone's workflow. Likewise, Cherry breaks XOR linked lists, but not too worried about that. We'll say, so some arguments in favor of why it's okay. Well, the results of following our rules is that you're reliably respecting pointer provenance. Your programming language expects you to do this. And there's a risk of things breaking in interesting and subtle ways if you don't follow provenance. Programming language, like implementers have been implying provenance since before the C defect report, and I think the C defect report was a result of of optimizers doing things that the programmer didn't expect. It eliminates some possible races and the sort of the mmap, unmap, remap thing. Changes are portable, at least in as much as any use of mmap is portable. So that's pretty good. And real stuff works. We got 50 to 100 million lines of code running under this framework with very little modification in the grand scheme of things. Running with full memory safety, with full spatial memory safety, with heap temporal safety, and in a still somewhat fragile but increasingly robust manner with every library being its own compartment. So, proof is in the pudding. And then on top of that, yeah, we get the compartmentalization. So, questions? And there's a question mic somewhere. So it's not like it's 64 bits of tag. It's that pointers are now 128 bits wide. Yeah.
And somewhere in there, there's extra information about pointer capabilities.
Yes.
When you revoke a capability on map, does that mean the kernel will go through every word in the address space that is allocated to the backing store and rewrite that?
So the way it works is it goes into the quarantine. So during the revocation sweep, which we do periodically, we walk all of the places in the kernel that might hoard capabilities. So KQ, for instance, can hoard a user pointer. We walk the registers of all the threads which have been stopped briefly, and then we walk all of address space in the background.
Okay, so
and
you do have to rewrite each word in the address space that has some backing store allocated to it.
Yeah, well, we rewrite every capability which is within the bounds that we're revoking. So we have a bitmap.
Hold on. So you're revoking some region, pages 3 through 7.
Yeah.
There are pointers to that region anywhere else in the address space. So you're revoking pages 3 through 7. But
Yeah.
there are pointers in the 3 through 7 anywhere in the address space that you've allocated anything. So don't you need to go through and invalidate all of those?
We walk through the address space and we read every capability, and we see if it is within the various bounds that we're currently revoking. So whether we're in those pages that are from unmap, or they're within something that's marked in the bitmap in malloc. And we walk through all of memory, and we clear the tag on every capability that's within those ranges. And we check that that's within the range by checking the base address of the capability.
Right, okay, thank you.
I wanted to ask a question about this replication process. If you have an adversarial process, how do you make sure that the process cannot snatch away a capability that should have been revoked by, for example, keeping it in a register while you sweep memory and then writing it to memory while you sweep the registers?
We do that by forcing all processes to the kernel boundary. So we stop them all.
So it's like a stop the world sweep.
It is stop the world once, very briefly, to scan all the registers and all the hordes within the kernel. And then we have a capability load generation count in the hardware. So there's a 1-bit generation count. We flip the generation, and now any attempt to read a page that has not been cleared and thus had its generation updated faults, so that you can't insert new ones into the process. Now, in the current implementation, as of our last release, there is at least one place where you can hide capabilities, which is in POSIX shared memory objects. I have a patch to fix that. It has a number of complicated implications, but I do have a patch for that.
That sounds like it would be safe, but would also possibly cause high latency spikes when the amount of ports gets very large.
There's no stop the world during the scan. Scan is done in the background because of the generation count.
Okay, that makes sense.
So from the initial cornucopia paper to the cornucopia reloaded paper, we went from high numbers of milliseconds in a maximum observed latency to microseconds.
Last question.
Could you block a thread which insists on reallocating something which was just unmapped until the garbage collection finished?
Not today. You could implement that.
Okay. So where do I buy a laptop that has these 128-bit pointers?
Well, I hope soon, but I would say that the first 64-bit processor that is likely to hit the market, as opposed to the Armadillo prototype, which is available, is probably going to be a processor by Codasip or some spin-off that does a test chip. They're developing an application class core, but not like laptop grade, more like, Pi sort of thing in terms of microarchitecture. So hopefully soon.
Thanks again.
Yep.
So when you scan for relocation, do you scan the physical pages or each address space?
It is an address-based thing. Capabilities about
Do you get any support by the
Hello, hello, and pardon my voice kind of putting up a fight, but hey, that's like the systems I'll talk about. So the title is FreeBSD in Windows environments, how FreeBSD is uniquely positioned to help deploy, virtualize, and serve Microsoft Windows production environments. My name is Michael Dexter. It's great to know many of you. I wear many hats. You're welcome to reach out to me on social media or in the hallway, etc. There is a paper you can copy and paste. This is a stealth tutorial, and that's up on the site. And you can generally find most of my things at callfortesting.org, notably the production user calls that you're all welcome to attend. They're completely transparent, talking about containers, jails, zones, and ZFS. Any users here? And yes, okay. Anyone not using ZFS? Just, okay. Yeah, okay, one. Out of here. No. And, of course, Beehive, the hypervisor. So this all started with a book. There was the FreeBSD Corporate Networker's Guide. Who remembers that? Anyone? Around 2000 for us old geezers. And Ted literally wrote the book, like metaphorically and literally. It's a great book. It laid out the whole territory. And Michael W. Lucas was terrified that Ted would suck the air out of the book industry for BSD. And he's like, wait, where's the follow-up? You sure? You sure? So anyway, a few things have changed since 2000. Jail had just arrived. It was like brand new in what, 4.0? SMP was a new thing. 64-bit addressing has come along, and UEFI-GPT, a complete rethink of all things system starting. Welcome, welcome. libxo and libucl have come along. Package has come along. It's described as one of the best package managers out there. Yes, package source is awesome and portable, and there was a great, was it Raven packets and ports that were kind of there? It's very cool. Packet filter, thank you, OpenBSD, and dtrace and ZFS, and Beehive and the Zen hypervisors. Who knew that FreeBSD has a fully working Zen hypervisor? Anyone? It's a thing. It does. Check, I have a little package in my repo. You can go try it. It quickly turns the system into a Zen host. It doesn't quite have Zen domains, but please test it to see if it's, up to the task. Roger's been great to work with. Anyway, a few things have not changed. The license, and it's protected by a foundation, so they won't pull like a Red Hat, IBM hat. Take it away, steal it. The user source, build worlds, you make build world. Nowadays we have like SMP, so make J, like 48, build world, etc. Ports and packages, that hasn't changed. It's a great model. It's not too draconian, it's not too lightweight, it's just lovely. It's a Unix environment with things like POSIX and a guarantee on TCP/IP and just those things that the whole entire internet runs on. NFS hasn't gone anywhere. SSH, thank you. There's a release, what, yesterday, today? Thank you, Damien and company. Control T, is there anyone not familiar with Control T? Anyone? Whew. My people. And the BSDcons, welcome. I can't believe the turnout. It is annoying to not have time to talk to everyone. It's like, wait, is that Dan? Dan's here, but Dan vanished again. Dan it. So, a few things have changed in the last year. BSD dialog. I lost track of this one, but the in-base dialog used for like sysinstall, that does a cute 2E little interface with next finished installation. It's now BSD licensed and not GPL, and there's another little baby step forward. I talked to the NetBSD person who had one, a custom bike maker in Portland, and he wasn't too active in it, and somehow various people got that going. Package base, just, it's here in 14. Just this last few weeks, I've gotten it working to have a script you can find in the repos here to blast out like a 15 package-based system for testing from a 14 host in a boot environment, of course, and off you go and roll back as needed and dual boot as needed or quintuple boot, because that all works really well. Mount-T nullfs, you can nullfs a file into something like a jail before only directories. That's kind of cool. Make image, make fs-t ZFS, meaning an unprivileged user can build world, build kernel, build a bootable ZFS on root boot image, and I have a script in the repo to mirror those both in software and hardware and push them out to real systems. I'll beat up on boot images later because they're awesome, but that's a very cool tool. There were a few bugs. Colin found one, I found one. They got fixed. Thank you, Mark Johnson, you rock. And Mav, of course. The images that came out of that, ZFS VM images, but they're just boot images, VM, whatever. They're just boot images as if a hard drive. They're great, they're raw. OpenZFS 2.2, things like the block cloning that has possibilities the ZFS call hasn't even considered. It's a very exciting technology, lots of neat stuff. GPU PCI pass-through, I'll touch on that a little later, TPM pass-through. Beehive on ARM64, someone donated me an old ThunderX machine, and boom, up came Beehive, and I'm impressed, I'm very impressed. So I have just published yesterday my talk from Fossey on FreeBSD on ARM64, and little did I realize to what degree they have zero hyper-threading, yet lots of cores. You can hand out cores like candy, like an old mainframe, and you can actually have some notion of a guarantee of service to virtualized customers. Here are your 10 cores, they're real, have a nice day. Maybe 8, 16, whatever, but it's a thing. And of course, Samba 419, which I'll get to in a sec. So it took time. FreeBSD 14 onward is really good. Some of us in this room, looking at Patrick, we've been very patient. We've been remarkably patient over the years, the bumps in the road occasionally. And OpenZFS is really good. And FreeBSD is the only OpenZFS in base OS to my knowledge, thank you very much. And Samba 419 supports a functional level 2016. That's essentially the modern Samba Active Directory level. Everything else is just little tiny add-ons and no big whoop. So I'll get to that in a sec. Furthermore, I don't mean to beat up on the competition, but do a search for ZFS init ramfs and hear the tales of woe, where there's some amazing performance and scalability of ZFS on Linux. Just don't update. Just leave it. Just don't touch it, because there are so many parts from different sources trying to work together, and there are some bumpy moments in that, and I sympathize, but it's like, don't hurt yourself in the process. As I just mentioned, I think FreeBSD is the only tier 1 OpenZFS in base maintained platform. You can bolt it onto other OSs like Mac OS and Windows, and I've used it on Mac for over a decade. This machine's running ZFS, it's a new MacBook, and et cetera, et cetera. And about that whole update pain, vendors have staff to deal with that. Hobbyists have time to deal with that. Production users in the middle don't generally have time to futz with it for hours or days to get back to exactly where you were yesterday with the new version of something. Not that I have any opinions on anything. So furthermore, the licenses have not changed and will not change. Looking at MD Markdown tools, they're generally MIT totally permissively licensed until they get good and they instantly go AGPL or something that moment. It's very strange how that keeps happening. But with something like FreeBSD, OpenBSD, et cetera, NetBSD with foundations, there are very few OSs with foundations behind them, may I add. They will pretty much stay with that license for eternity, which is great, meaning you can rely on it, which I like relying on things. I do. From the FreeBSD Vendor Summit last November, there's a Linux driver for everything. Great. Many of them are just reference drivers. It's like, well, this is not for production. It's just like a hello world driver for the thing. That's not helpful. And doing a decade of TrueNAS support, TrueNAS scale customers are coming along. If you're pushing limits with like 100 gig networking and fast storage, somehow with at least versions from 6 months ago, there was a solid 20% performance loss off the top. It's like, well, I kind of need that 20%. I paid for the hardware. I want my hardware's delivery. So whatever. But it scales. But they remove much of that. So it's unique. Talk to Patrick here. He will. I'll introduce you afterwards. And when it comes to platforms and solutions and appliances based on GNU Linux, the world doesn't need yet another GPL violator. And to their credit, bless their hearts, IX systems with FreeNAS, TrueNAS have had a completely 99.9% permissively licensed solution that arguably is completely GPL compliant, sharing all the sources, the build tools, and all the stuff that GNU Linux is supposed to be promising and enforcing. And it's like, okay, because we're Unix people and we just want stuff to work and help each other. So Windows, let's talk about Windows. Yes, I'm going to talk about Windows. It is the best available API implementation for Win64 API. And it's used by many business applications. I don't know, AutoCAD, let's just say AutoCAD. It runs on Windows. Yeah, it used to run on Mac. And it generally has, okay, to its credit, very vendor-tied hardware drivers. So yeah, you might get the best drivers for Windows despite the OS, but at least the hardware driver is kind of good, and random other features. So a few things have not changed over the years. I avoided Windows professionally for a decade or two because, hey, as a Mac person and a Unix person. Well, oh my gosh, I have arthritis right there from the Beehive testing tools from like 10 years ago, because on a Windows keyboard, they put control over here or over here, maybe here, instead of a command key, which is under your thumb, and you don't get arthritis there as you're kind of frantically programming in shell to make Beehive more usable for all of you. So somehow PCs have random placement of keys. Not good from an ergonomics perspective. Date stamps. If you copy your 2019 tax records to another directory, you might get today's date. Maybe, I don't know, just rando. That's not cool. Let's see. Refreshing folders. You copy to a folder from elsewhere. It'll refresh when it wants to refresh. It's not up to you. No, you can manually refresh like 20 years ago, but fine, okay, fine. Oh, the sorting order, it's like alphabetical is not a thing. You get like folders and files and why? Fortunately, Windows is completely GUI based to make it super easy for everyone, except when it's not, and you jump right into the registry with some like hex values you throw in the thing. It's like, wait, but you just, yeah. So Windows PE is the thing that, pre-boot, I believe, environment, that pops up when you're installing. And it's got the Windows 7 window dressing. It's like, oh, really? I thought this was Windows 2025. But yeah, whatever. And the whole OS is mapped to XML because you have the full configuration pushable to it, but you can't just save off the config, which would be really handy from the working system because reasons. So yeah, and of course, it's XML based except when there's something you need that's not covered by the XML coverage. Okay. Oh my gosh, PowerShell. Has anyone dabbled with PowerShell? And I swear someone like watched a Unix user over the phone and had a friend describe it. And like, you type these commands and stuff happens. So they did like ls for a file. And so it's like, I think he said list files. And it's like spelled out in like camel case. Like, no. And how many human years have been wasted typing administrator instead of root or admin? Like, just it's simple. Or misspelling it or mistyping it. Pro tip, not everyone is a native English speaker. Just saying. So a few things have changed. The whole product gaslighting, arm twisting of there is only way to back up your system, and that's with our own OneDrive or Azure services. And they literally use a phrase, oh, there's cloud-based backup. We think you'll like it. That's a technical statement in an operating system. And the whole good cop, bad cop, I just installed on the OS, but oh, your organization's policies don't allow that. It's like, me and my hammer. No, no, you do what I ask because it's a fresh install. How is there an organization telling? So there's that. Oh, right, and they're considering spying on you like crazy and having the most privacy violating, perhaps discovery problematic technology in human history, legal discovery. So I won't even go there about Microsoft recall. So all that said, Microsoft Windows must be contained to have any sanity, and FreeBSD is really well positioned to do so. And having such good OpenZFS integration in FreeBSD is really important for the reasons I also touched on earlier. So deployment. So Windows is consumerish, business-ish identity crisis OS, and it's really gun-shy about giving you useful information. Is my disk healthy? I occasionally want to know that on an old machine. And at best, you can squeeze out a global smart value, not detailed values with like special WMIC commands and et cetera, And as a Windows Server product for industry, for enterprise, and blah, 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 it also holds back a whole lot of information you really rely on, or makes it really hard to find that. So I'm of the opinion that hardware facts should not be secrets. And booting a Windows machine once you've disabled secure boot into, say, FreeBSD. You can have things like DMID code, which will list a whole lot of parameters, including perhaps even memory module brand and serial number and capacity. So if you have to order more of them, you don't have to like go down to the data center, rip open the machine and stick your head in it to see what's in there, or try to find a receipt from years ago that's probably not accurate. I don't know. ACPI dump to grab Windows keys, and a colleague is looking at adding Windows key support to the FreeBSD in base ACPI dump. That's kind of useful. Linux, with all of its virtual file systems, has like dev/dist/that stuff, which will eventually give you a key, which is kind of cool, but there are ways to do it with a bunch of syntax. Disk info is a very simple tool built into FreeBSD that gives you some block size, actual size, you name it, serial number, basic info. And of course, from third-party ports, the Smart Control utility, which is pretty universal in the industry. Chuck kindly produced a prototype Smart for FreeBSD for consideration in base. Go see my talk on the subject. And if you have Smart Control and Smart Mon tools as the package, on Windows, they use Linux device namings like dev HDA, and I don't know which one's trying to pretend it's the other, but it's a bit surprising. So you can get that information. And there is a tool, WMIC, which is a Windows tool for dumping stuff, and your mileage may vary what you squeeze out of it. So I, in the course of this, spit out a simple utility on my repo. Check out this repo for everything I mentioned earlier, github.com/Michael Dexter. Not endorsement, but is a useful tool of GitHub. And PCHW, which, for example, will poke at a laptop and give you, from DMID code from the low-level firmware, the actual product name, which can be different from the name on the top, on the lid, BIOS revision, serial number, CPU, asset tagging. Useful stuff that might be stunningly difficult, or you only get through event, like HP support utility will give you maybe some of that on your new HP laptop. It's like, no, I want to go right to the same spot on every machine. Thank you very much. So, on the theme of those facts should not be secrets, NVMe control is built in FreeBSD base, and you can reformat an NVMe drive in an instant to go from, say, 512 bytes to 4K. NTFS doesn't do much better on 4K. It's a kind of a wash, but on, say, a real file system, you want that. So it might be possible to use dev control to detach the device and reattach it and see the new block size. Frustrating on a NAS if you're trying to change block size and you have to reboot to see the results, but that might do the trick. And of course, changing your block size will wipe your data. Do be very careful about that and know what you're doing. And when I bump into a Windows machine, the first thing I do is image it before even seeing its overall health. I don't care about it. I boot it in FreeBSD and start imaging. So CamDD is a built-in FreeBSD native stack DD utility, disk duplicator, I guess. And gee, when you do a big old disk, it always gives you the exact blocks, whereas DD might round it up, or I guess hopefully not down, but you get what it lists in disk info. Like, that makes me comfortable. I don't want like surprise blocks tacked on for reasons. Now, in ports and packages, there are sysutils DD rescue. DR rescue? Oh, I lost a D there. DD rescue, as per the example. That is a forensics DD that will retry and keep track of where it's going. So if you have a drive that's overheating, it'll image it to a point and keep track. I went this far, and then try again after you've let it all cool down and blown on it and all that. So the moment you get that image, drop it on ZFS, snapshot it, perhaps boot it in a hypervisor, but that's a different conversation. But that gives me, with a very cool Windows-based client in my hometown, a lot of control. Oh, I see a camera coming up. So, at an extreme, there's something called Clanet Recovery. It is proprietary. It does RAID recovery. I aimed it at a HP RAID array that burned up. Literally, the controller burned up, and often the config is burned in the controller. Or ZFS, and I've had remarkable success, and I've run it on true NAS systems under Beehive, recovering pools and Windows arrays, etc. It's your friend, but this is not an endorsement of proprietary software. I've seen a few disparaging comments about gpart, but of all the partitioning tools on planet Earth, I really like gpart. It's the native FreeBSD one, and gee, Apple made it into GPT on their system, and it no longer works thanks to all the security policies, even if you turn them off. Don't ask me how I know that. ZFS on an M1 Mac. And wow, gpart destroyed -F, capital F. It destroyed the partition table. Yes, that's bad if you don't want that, but it's great if you want it, because Windows and Mac really don't want you to delete partition tables. There's just some unwritten rule that it's going to put up a fight, and I've gone mad maybe with like the disk part at the command line in Windows, but it's frustrating, whereas I can do it predictably in seconds on FreeBSD. I like predictable in seconds. So finally, it's a bit of a mixed bag that your firmware utilities for your HBAs and other things. Yes, maybe Windows has the only tool to update your firmware on your laptop or something. So yes, use that. Such is life. Avoid that trackpad firmware on your AMD ThinkPad because, wow, it became unusable under XFCE. That kind of miffs me, but such is life. Who's had a whole bunch of EFI boot entries show up where it's like FreeBSD, Debian? No, Ubuntu loves to just hang around. It just embeds itself and it'll be there for as your hand go up. So with just a few commands, it's not super intuitive, but you can list them, you can delete them. And it's like, boom, I don't want the first one, which happens to be whatever. Just do it in seconds predictably. NTFS partitions. Yes, there's fuse-based NTFS. Gee, Kirk, who just spoke in the other room, wrote the book on overriding file systems, modern, fast, overriding file systems, of which NTFS is one. Okay, so yes, they still use that somehow, and you can mount it not super fast, but reasonably well on FreeBSD, which is useful for the things I need to do. And you can also natively share, you can natively mount an SMB share with mount SMBFS. It might only do older versions of SMB. Some people get really upset about that. If you don't know how to secure a protocol with, say, WireGuard on the LAN, you might not want to be in networking stuff. So it's a basic utility, and the Enterprise Working Group from FreeBSD Foundation has been talking about updating that and other tools, and the in-base, I believe, is no, in-base client. Okay, so yes, you can mount also SMB shares with FuseFS SMBnet, which I believe relies on Samba, which is like the real code, but in Fuse. So it's a little slow. The syntax is confusing as heck. The slides are up on my site if you want to get that exact syntax, but it works. Back to deployment. This was a little more on setting up that bizarre Fuse NTFS. It's a thing. I did the hard work for you to try that. And then finally, copying files. You'd think that'd be real simple. I mentioned all those dates getting lost, so at least there's a classic Windows utility robocopy with a whole bunch of flags violating every OpenBSD, make it work with same defaults right out of the gate. It will eventually both retry and preserve dates. What a concept. So there's a syntax to do that from 2 directories. Thanks, guys. FreeBSD now has OpenRSync out of OpenBSD, but it was a little bumpy the last time I tried it. Thank you, Kristaps, for that. BSDLV for the win. BitLocker. Yeah, Microsoft self-imposed ransomware. Warning, there are laptops that will ship with both BitLocker enabled, and an online update for, say, the firmware might wipe out the firmware keeping of your keys. They don't prompt you to save off printable, to their credit, printable keys and such. But you might get fully ransomware without even knowing it. Thank you, them. But there is a tool to BitLocker unmount a partition, for better or for worse. So a concerning technology has some amount of help. Oh, okay. So yeah, after looking at storage systems for a decade, yeah, use any encryption with extreme caution. You're usually your own worst enemy. And I've heard people like, oh no, my pool won't import. So I'll just quickly keep recreating keys and stuff. It's like, no, that's not how encryption works. So yeah, I just mentioned the horror stories of BIOS that nukes your keys for you free of charge. And there is no recourse. That's it. If you had a backup, great, on Azure Cloud or whatever, OneDrive, blah, blah, blah. Okay, so funny, one of my laptop displays burned up 2 days ago. So carry these like USB to NVMe adapters. Yeah, Albert and Back had a really nice one that saved my bacon this week at the conference. And so the ability to pull an NVMe drive out of machine and image it and then work on it and tweak it and do all the things is a really nice feature. Of course, a USB attached NVMe drive will not allow for, say, the NVMe control to change the record size. It'll just show up as a USB drive, but hey, such is life. Bad Apple, bad for soldering and storage, because I'd rather just pop out an NVMe drive and do useful sysadmin stuff. But I do have a tool. Imagine, because as I touched on briefly, VM images are your friend. The FreeBSD release engineering team, and sorry to do a fire hose, but that's my style. Hopefully you've been warned. The release engineering team produces VM images that just happen to be raw boot images, and I have a tool to splat those out to a hardware device. Super helpful for all the administrative stuff I just mentioned. You can keep it mounted and throw package at it, because PKG on FreeBSD is smart enough to say, oh, this is a FreeBSD 15 current ARM64 system, I'll put the correct packages in. What a concept. They get a pat on the back for that. So, about those boot images. Debian and OmniOS have cloud images, and people get hung up on cloud, but it's a raw boot image. It's like a disk. That's it. So you can put it in hardware and it boots miraculously. So that same tool also supports those OSs, and since I last gave this talk, Router OS. And I've integrated Windows. You can use an auto unattend XML file, which is a layout of what you want it to do and create users and do stuff. And I used that a few days ago to update the firmware on a camera to test at this event. I just splat out an image with all the stuff like secure boot and cloud requirements turned off, and added the one utility to update the firmware, did the thing, and then just dispose of it. So very, very useful. And what do you know, if you're relying on, say, Windows, which kicks off auto unattend XML from like an ISO file, which it repackages for you based on ancient Beehive knowledge, you can boot it under Beehive, create a bootable disk image, because it goes to that first step configuration, and then you have the image you want, which can go to hardware, be expanded, can go to a VM, all the places, because it's just a boot image, nothing more, nothing less. Anyway, I love this, it's so useful, and you then eventually boot it under a hypervisor if you want. So, deployment. I used that strategy to update some firmware at this conference. I like being in control of systems, not working on a new Windows system, and if you accidentally let it boot into the on-disk OS and it spins for 20 minutes configuring, doing something, despite the fact that I'm about to change the block size. And so I put in profiles for Windows 10 through 25. You can download the insider preview of 2025 and boot it on Beehive. It's just, once it's contained, it generally stays contained, so that's kind of cool. In those config files, you can enable RDP, I love a user root because I'm just hitting all my same systems in the lab, key point in the lab as root. So it's a root user on Windows. SAC, super useful. It's a management console in Windows Server and possibly even Windows 10 and 11. And it's just, you can get a shell. That's very useful in minutes. So finally, I was this week thinking, wait, just about every OS available from every vendor has OpenSSH. Thank you, Peter and company, OpenBSD team, because Windows has OpenSSH. Mac has long had OpenSSH. Every GNU Linux distro has OpenSSH. Maybe someone has Mosh, I don't know who. And every BSD has OpenSSH. That is the most pervasive open source software on planet Earth. Thank you very much. Good work. So you can go a step more Windowsy with XRDP, the RDP client. You do require the GPU driver from Tiger VNC server. That's not super intuitive, so I put it there. And RDP, which is like Citrix Magic, is pretty darn cool. It does like sound and keyboard clipping stuff, and it's real efficient, and it's pretty darn cool. So here are the steps. You can rip them out from the, bless you, rip them out from the slides. And there's also Ramina, I hope I pronounced that right. It does support VNC and RDP and a bunch of things. So there are clients. So you can sit on your Unix workstation poking at your Windows machine under the BSD hypervisor. It's like, okay, that's contained, bless you. So speaking of virtualization, Beehive has supported Windows since 2015. I will never forget, in Stockholm, who was like, you know, FreeBSD just needs Windows support, and maybe it was like LLVM or something. He's like, oh, just hold tight, there's a demo in a few minutes. So yes, there is Windows under Beehive. It used to be really quirky. It's down to just a few things you gotta do, like have the LPC device on slot 31. Yeah, okay, and most other OSs don't care, so just make that your default. That's a whole different topic. There was a great Beehive tutorial earlier this week, yay. TPM pass-through arrived on 14, which is the hardware TPM on a machine, the trusted computing module thingy, to go into a guest OS. Thank you, Beckoff, for doing that so that you can have true BitLocker on Windows VM, all the things with Windows never knowing any better that it's completely virtualized. Same with GPU pass-through. It's a bit few rough edges, but Beckoff has been working very hard on that. And just like 2 weeks ago, TPM emulation showed up in Beehive following the QEMU model. And having a secure store that perhaps you can even push read-only to a bunch of hosts could be maybe useful for SSH keys, for ZFS encryption keys, and a whole bunch of stuff. So I'd hope that TPM is usable for a lot more things than BitLocker, which I beat up on quite a bit earlier. So yes, that is a technology directly out of the production user calls. There are 3 calls a week I think I touched on earlier, so I'm not here to talk about those. And virtualization. And stepping back from conversations this last few weeks, all discussions of Kubernetes and Docker and the thing and the expanding multiple tar files on top of each other, blah, blah, blah. It's like, oh, you don't have a real file system. Oh, no, we don't. So on ZFS, all that virtualization and containment is suddenly just kind of natural. You can snapshot, you can clone, you can roll back, you can do many things that just aren't available elsewhere. And suddenly all those contrived technologies dancing around that problem make sense. So I will say, hey, friends, don't let friends use Windows without OpenZFS as the backing storage. So virtualizing, I'm sure, I think one hand went up for not using ZFS, or that was the second one. So everyone's pretty familiar with it. It's great for mitigating ransomware. Rollback is needed. User error, deleting files. Clone a snapshot, mount it, or grab the file for them and have it magically show up and they thank you. You can roll back the whole OS. You can roll back a whole pool with a checkpoint. It's magic. Staged OS deployment, I'll get to that in a second. And data recovery from multiple sources, not tape, actual disks that are spinning. So here's a true story, super quick. A client has a proprietary Windows bookkeeping package, and it's a whole lot of Windows database controlling it. And with each update, you have to like update the database format and all that. So the choice is, gee, I go from like 4.2 to 4.3 and update the database in the process and like at which point I realized, wait, if I just go through the update process, roll back the actual OS, keeping the fresh database, fresh install of the new application, import the database, and like it's a fresh install based on a 5-year-old set of data. That's cool. That is normally a long, painful afternoon on other OSs. Eyes on the prize. I touched on this, the GPU pass-through and the TPM pass-through from Beckoff. He gave a great talk last year in Coimbra. I will keep pounding my head against that. I might buy their same hardware. So if a Windows desktop boots to FreeBSD ever so briefly and has full graphics emulation, full graphics pass through and keyboard and mouse, et cetera, the user will never know that there is a proper OS under the hood snapshotting all the time and replicating it elsewhere. And yeah, try replicating a Windows or Mac system continuously. I guess Apple's cloudy thing is not bad. The restores are ridiculously slow, but I don't know how else to do it. And I kind of buried the lead on that whole Microsoft pushing all their cloud storage. Try finding a competing backup tool in the Microsoft application store. They're all gone. You will not find Veeam and all those classic little proprietary ones, all gone. That's pretty monopolistic and not kind. Anyway, so backing that with OpenZFS is like, I get to sleep at night. So suddenly those Windows machines are snapshotable, sendable, and Beehive bootable. And if your office burns to the ground and you have off-site backup, like Estonia with having their entire e-government backed up in Liechtenstein, you boot the entire office on the servers at the backup site within minutes, not trying to recover from, what, tapes and whatever else for weeks. So no, no, never again, never again. Serving quickly. So Windows has amazingly good fiber channel and iSCSI support because the built-in file system, network file systems were so terrible, CIFS specifically. So I've heard of systems booted from iSCSI surviving the reboot of the iSCSI host. They just cache everything up and like, oh, you're back, thank you, cool. So I got the syntax you can rip out from the slides on simply creating a CTL, the CAM target layer, FreeBSD native iSCSI and fiber channel contraptions. It's there, it's a thing, it works. Thanks to FreeNAS, TrueNAS, petabytes and exabytes have passed through that. It's proven code, it's efficient. Thank you, Mav, for making it awesome, yay. You can validate your config, but I mentioned boot images. I like boot images, even if it's just a big old image in a data set and shared off with iSCSI because it's a block device, no more, no less. If it's a block device over iSCSI, you stop the sharing, you mount it locally, you boot it elsewhere. It doesn't care. It is complete liberation from being tied to hardware. I love it. You can mount it in NTFS3G, loop back mounted with mdconfig. ZVols, not so much. They're kind of stuck on that pool. It's like, no, I like copying files. And there's nothing worse than someone coming across a TrueNAS system. I have a petabyte of storage, but I don't see anything. So it's a ZVol, and if you know where to look, it's over there. But if they see this big file, that makes sense to people. I like that. Another fun fact, Windows has NFS support in the enterprise versions and stuff, and someone somewhere, maybe in this room, got it working. I didn't want to go there. Samba. So the server message block, the classic Windows networking, for better or for worse. Thank you, EU Commission, for like getting them to open up their protocols a few years back once they were declared to be monopolies and doing bad things. So there's that. Samba's complex. Last count, there are 101 individual utilities in Samba. I'm like, oh my God. But there are 3 simple commandments to follow. All the DNS jokes apply. Make sure it's your primary DNS and verify your DNS before you do absolutely anything at all. Keep time in sync, and then it's obscure stuff. But usually it's the first 2. So Samba has been able to be a domain controller for quite some time, which is nice. Samba's been able to be a level 2016 controller since, I think, 219 or whatever it is. So that means we can finally have meaningful Unix-based FreeBSD, OpenBSD, you name it. I'd prefer you have a super awesome file system-based domain controllers, and I've got people running those in production. I'm not yet running my own in production, but darn it, I have a simple script that asks you questions and blasts one out. Please try it. Aim it at your network on a test machine and get back. And then looking back at my talk on FreeBSD on ARM, so Windows Server will support ARM64 at some point, and it came up earlier today, and it's like, yeah, maybe someday, yeah, maybe. And well, what if you're in Germany or somewhere where power is ridiculously expensive, and you care about every watt, and you want those cores you can just give away like candy? Well, if you've got your Active Directory on an ARM64 server, you might have a whole swath of security advantages, because as people try to hit all those classic little Windows hacks on it, like good luck with that. And that's really nifty hardware that's coming online. And Ampere is definitely one to watch. And I think it was Andrew Turner gave a great talk on an update on, 10 years of ARM and FreeBSD. Check the stream for that. And some field notes, because there's a little tiny bit of time. Daniel, who's been active on the production user calls, has produced Zelta. He used it many years internally. It's an awk-based, extremely portable replication tool for ZFS. It's awk-based and a few shelly things. You don't need the matching tool at the destination, as long as it's a POSIX OS. That's cool. He does not use the -F force flag when backing up, deleting data in the process of backing up, because if you're using a force, you are admitting you failed. So no, it's extremely enlightened. He was super shy, didn't come to events, and now he's been at BSDCon, and he's a total community animal. I love him dearly. Okay, 5 minutes left. Let's do this. So MAC addresses are your friend. You can fake them, and having them as DHCP reservations is such a lifesaver on a LAN. And I know visually that the third machine over has this IP address simply because the MAC is always the same regardless of OS. Yay, love it. And oh, Proxmox, you'll see that article that no enterprise system uses DHCP. It's like, well, no, well, DHCP with reservations, yes, they do. Stop making it hard to implement that. So I won't talk about it. So in Taipei, in the frustration trying to find those GPU pass-through machines, I created HipScan, a bit like Angry IP Scanner, super useful, but happy IP Scanner. So I haven't figured out all the situations where it doesn't see stuff, but it's super useful for like when you have a headless virtual machine and all you have is a MAC address and a table, it's like, oh, it is alive or not. So quick thing, if you're on a Windows machine and you don't want to be AD joined, you can actually do a / in the username, and it bypasses all the AD stuff. That's something I learned along all of this. And as I mentioned, there are the trifecta calls, production user calls from callfortesting.org. All are welcome. They are completely transparent. The agenda is wide open. You can put a topic on there. You can sit back, have coffee elsewhere, and we'll probably discuss it. And you can come back and watch the video or read the results, both of which are out public. And you didn't even have to attend the meeting. It's great. So looking to the future, OpenZFS on Windows. Jorgen, who did Mac OS support, has been doing Windows support. And wow, did he blow minds at the Developer Summit a few years back. I was the first person to use it on real hardware. He had never gone beyond a virtual machine, so there had been little bumps along the way. And I don't know much about, I believe it's ButterFS on Windows. However, it lays out what root on ZFS would look like for Windows. So take a look at that repo if you're really feeling spicy and you want to bring that over to OpenZFS, because that could be a real file system on Windows, which I'm talking about some rather useful, enlightened workarounds. What if they actually did it right? Just saying. So you find your device with the funny device naming, and then you do things like a zpool command, and off you go. And so thank you. I appreciate that. I hope you've enjoyed this fire hose. It's a stealth tutorial. All of this is in the paper and the slides. And I hope I saw some cameras pop up, and like, okay, I hope there's something useful for you, and I'm totally open to questions for the next few. Yes, Peter, a microphone for you. Oh, yeah.
I have a question.
Yes.
Have you tried to export that ZFS disk as a Samba share in a Windows domain?
The question, hopefully is on the stream, is have you exported that, was it an ISCA or ZFS disk in which regard? So at the file level, as in a data set from, or a block device? Yeah. So fortunately, thank you, FreeNAS, TrueNAS. They do that 24/7 and have for a decade plus. So that's an absolutely fundamental function of TrueNAS, is to be AD participating, if that answers your question. As for independently here, yes, it should work. I've used a Samba share, actually, yes, AD attached with my own home-rolled Samba server with a client in production, and no user knows except for the occasional locking issue, but maybe there's a flag that'll solve that. Yes, I hope that helps. Have I found a sane way to back up Office 365 to ZFS? Whew, SharePoint environments. So I've not dealt with SharePoint directly. However, a virtual machine, for example, I mean, even just a parallel example, on a Mac with iPhotos, which has this weird databasey thing, if you use the Windows client as a Mac user, you get like directories of files that make sense. So having clients for, say, Dropbox and Office 365. I hope I've mapped out how you have ZFS as close and as high up the stack as you can. If it'll back up to a network share, you can clearly share that with, and snapshot it with ZFS and Samba. But I personally have not done Office 365 and SharePoint. So it'll 300,000 files or 300? Okay, so after a certain number of files, it tips over, and it'll back up elsewhere, but not ZFS. Sounds like a Microsoft issue, but I'd be curious, can you segment your data so it's just split it in half and team here, team 1, team 2? Catch me in the hallway afterwards. I am curious because it's like, this is to make your life easier, not harder, so let's continue that theme. Other questions? Yes, to the microphone, just one sec.
Have you ever tried transferring one bare board machine Windows into a BI VM? Like take the whole thing and put it into BI, or from other virtualization to BI?
Okay, the question is, have I virtualized a hardware virtual Windows machine? With the exception of BIOS boot, classic MBR, and you'll see that my scripts now have QEMU tools so that on a fast machine it's not horrible. Absolutely. And when I talked about very early on imaging any new machine I come across, it's specifically for that. Because when it's Tony's old laptop with who knows what, I want to see a disk image in a directory that I can mount or boot. Now, with this same client I've mentioned a few times, they were on Hyper-V. And I brought their domain controller over with QEMU image conversion to a raw file, and it came up in Beehive. I made a point of using the same MAC address, same RAM amount, which shouldn't matter much, and same CPU topology, because I guess there can be machine IDs that you can like fake in Beehive, and I didn't do that, but it worked. So no, that's worked really well. So I do the aforementioned bookkeeping application in Windows 2019 server, and an old 2016 domain server that I don't want to touch until I replace it with something it can kind of synchronize with and then ditch it. That's worked really, really well. Of course. Going once, going twice. Thank you. Thank you, Peter.
From the organizers.
Thank you so much. Tack så mycket. Tack.
originally going to title this talk Malware and Crypto Mining as a Service, because that's what continuous integration really is. But then I thought there'd be a lot of disappointed people coming to find out the talk wasn't actually about that. But in the back of my mind, that is what frames all of this. How can we build CI that is secure, simple to use, and obviously works natively on FreeBSD? It's a work in progress report. It's going pretty well. I originally implemented it as a set of things that I found hardest, and that was a lot of fun, but the list seems to keep growing longer. But anyway, onwards. So scratching the itch, the general idea, how can we foster an open CI, thinking more about why are all of our CI systems relatively closed, and then we dive down into some technical details. And a bit down at the bottom, I'm not going to talk about this, it's an entire talk all on its own, but distributing and processing multiple concurrent tasks is fundamentally a difficult problem and an interesting one. So scratching the itch, FreeBSD has great primitives, ZFS, Lua and base, pf, pf.conf, jails and beehive. Obviously building a CI on this amazing system would be trivial, and it should have been done by now. So public CI tools tend to have the BSDs as an afterthought, and we have shims and ports, we have documentation fixes, we have special workarounds on blog posts, but none of it is actually done natively, and anyone who implements one finds they need extensive scripting to leverage them. So we want to fix that. And the general idea is a FreeBSD native CI for the discerning Unix user, which obviously all of you are. C for the fithy bits, and more Lua than C. And the main reason for that is, those of you who know me well will know that I'm not a C developer, but I can do a convincing job of pretending to be a Lua one. Lua is a great little language, and we'll talk about that later on, but we want to use all of our FreeBSD toys, and we want to start off from little embedded systems, pizza boxes, Pi Nanos, that size of thing, right up to big servers, your typical CI. So that means our protocol for talking to the hardware needs to be pretty small, pretty simple, this sort of thing you could implement with a couple of shell scripts, but it also needs to scale right up to the bigger boxes. You should be able to use what you need, and it should be extensible to other operating systems as well. The very end goal is should be FreeBSD package install, and we're ready to go. That's where I want to get to in the end. So fostering open CI. Why do I think all of these other open source CIs are not really open? And that they are from a software point of view, but they're not open from a, could I take these Lego blocks and build something else just for my needs out of them? That's not the same thing. So all of the CI tools will have the same general architecture. They'll have an agent that runs on some sort of box, and it will run code for you, and then they will send messages back up to some other thing that has a pretty web UI. But that bit and that bit, the interfaces are all opaque. They're not open, they're not extensible, and if you wanted to write your own client to fit into it, you would have to write a lot of Java probably. Okay? So we need to get these interfaces right, and they need to be clear and documented, and they need to have some sort of schema so we can version them. Ideally, it would also be pluggable, so we can put extra bits of code in when we want it, and the goal for me personally is that inside the CI, the components such as how do we mount file systems, how do we make images available, each of these things is a small, easily understood script that can be replaced at will on whatever operating system you choose to implement this on. We should be able to re-implement the agent and the transport, and indeed the user interface as desired. So if you're doing this on embedded hardware, you're not going to use WebSockets, you might just use a serial console. If you're running it in a big data center, you might have special transports to shift really large images around. Some of the people I've talked to, every CI build results in about an 80 gig image, and they don't want to shift that around over a serial console. So part of the community aspect is something I've thought a lot about. So in FreeBSD, we have Discord, IRC, mailing lists, we have a forum, etc. And I've probably forgotten 3 or 4 other places that people will bug me about. That's normal. Human beings have different ways of communicating. But my general observation is you need to have a hub. You need to have a place to go that says, this is where we live. We want real-time chat. Everyone uses that now. But we also want a searchable forum. And from my experience in the Apache Foundation, having that online preserved forever is really, really important. And it's really frustrating to come across a project that had a mailing list or had Slack, and that information is gone. All of that expertise, all of those questions, all those people answering the problems that you now have is lost. So we don't want that. But more importantly, any project needs community, and that in the back of my mind is first stage, build the interfaces. Second stage, figure out how to get community involvement. Once I have all of these bits working together, I'm in a position to come back and say to people, how do you use this? What would you want differently? And how do we evolve that? And we want to do that in one place, in public. So, overview. As I said before, most CI things have an agent, and while this is designed to scale down to a serial console, the main version just listens to a WebSocket event. It's really common now, it's very easy to write, and in almost every programming language you have a library that does this, probably out of the box or easily accessible. So we have protocol sending messages forward and back. We start up, and the agent will register itself. It'll say, hey, I'm an ARM64 box. I'm running FreeBSD 15 current, and I'm interested in jobs that, I don't know, the chocolate jobs and the beef jobs. Okay, so per project targets, and each agent then can be selected to say, okay, the first stage is beef, everyone gets their main course, and then after that, then we do the chocolate ones. And the agents just need to register their capabilities. It's up to the server to decide how to allocate their resources. The agents execute a job on request, and most of us will have written shell scripts, make files, etc. And we know that we're going to have environment variables, we're going to have security keys, tokens, all of that sort of stuff. All of that has to be made available. We might need Git credentials for cloning repos, and we might have pre-encrypted secrets, which we'll touch on later on. Fundamentally, we'll be streaming a lot of logs back over WebSockets to a server that displays them. So there are quite a few security considerations on how do you allow an untrusted crypto miner to send results back in such a way that there's not a way of attacking the server or causing a denial of service. That's a difficult problem, and I've only solved part of that yet. I haven't solved all of it. And then finally, at the end, we're going to collect some artifacts, not log files, they've already been sent, but a tarball, a package, and we want to move them to a central location so that we can use them in a subsequent step. So we're chaining these things, do a job, have some artifacts, now do another job, maybe on a different queue, and have some artifacts again. A great example is, first task is to fetch the repo. The second task is to build the software. Out of that, I get an artifact. And now I want to distribute this artifact to production servers. So I'm going to have a final agent sitting out on maybe in a jail or a container on some production system. And it needs to be able to fetch that same artifact and then deploy itself and restart. And finally, we want to run sandbox Lua scripts at each stage. Sandboxes are great. On the server side, it's going to handle incoming webhooks. Pretty much the de facto standard today for receiving build requests these days is a post commit git hook. And it'll either be a local job. If we use not Game of Thrones, Game of Trees from OpenBSD, it now has support for this. You can get a signed webhook from GitHub, GitLab, and almost any other software 4G kid name does this. We also want to accept, though, direct submissions. So we don't just want a job that comes from a commit. We might also want a job that says, let's start from scratch. I want a vanilla system, an empty file system, and I'm going to put things into it. And for people who build operating systems, that is often surprisingly common. We don't have a concrete Git repo to start from. We want to make that base system from scratch. Once we have that based system, then we're going to use that in subsequent builds. So you can think of FreeBSD, new FreeBSD release comes along. Our first job in our CI system is going to be make the base, the vanilla FreeBSD container. And once that's done, then we're going to use that container as our future images for all of our software on top of it. Now, inside this Git repo, we will typically have some sort of config file. I'll come back to what UCL is later. So you can think of this as a YAML or a JSON file, and it says special things. I need this flavor of image. I have these tasks I want to perform. I have these secrets in here. And it turns it into what we call a DAG, a directed acyclic graph, which is a fancy word for a tree that doesn't have a loop in it. And some of these tasks will be run in parallel, and some of them need to run in series. And one of the nice ways of representing this is a big blob of JSON. Anything that's in series is an array. I don't know if this comes out on the screen, but that's actually a left and a right bracket. So an array has to be processed in sequence, item 1, item 2, item 3, it's a list. Or we can do it in parallel, and we represent that as a JSON object because the keys are unsorted. So we just process all of those keys at the same time. And we can combine these two things, steps in series, inside that some parallel steps, then another step in series, and keeping going underneath that. So directed acyclic graph, that's your homework for today. The server must have zero knowledge of keys and secrets. It's a web service, it's the most easy thing to compromise, and we want to make sure that there's no way from the agent for the server to get the secrets. That's really important. The server also must not touch the source code. We're going to clone a repo that we don't have any knowledge of. It could be very big, it could be very small. It might have post-receive hooks included in it that might run malicious tasks. So we don't want the server doing any of that. We're going to push all of those problems to the agent. We're going to restrict its CPU, restrict its disk space, and if it blows up, the server keeps running, managing other people's jobs. And finally, the server has to store the logs, the jobs, the job history, and the artifacts. So I'll switch in a second to a picture that's easier to read, but we want the overview here. There is a protocol between the agent and the server, and because this is the bit that's most likely to be re-implemented, we want it really, really simple. Now, without my glasses, I can't read it either, so if we've done this right, this will be an SVG. Whoops. Cool. The working name for the project currently is Zen, but I think someone already registered a domain called ZenCI, so I'll have to change it. On the left, we've got an agent. It starts up, it's going to register with the server, and it's going to send some capabilities, which in our world is just a simple set of key value pairs. OS is FreeBSD, hardware is ARM64. The server then receives that and will confirm the registration, says accepted, and then the client is just going to sit here and wait for requests. So let's go down, and we've got two nested loops. So from the server side, so the client will say, hey, I'm ready for workflows. The server will send a little JSON blob back, and it has an ID for a job, a ref, and a URL, which we'll look at later. That's enough for the agent to fetch this source code and work out what exactly are the next steps it needs to do. And then there's the inner loop, which does all the work. We've now got a job. We know what we want to do. We're running make, obviously, because that's what BSD people do. So we're running make, and there's a stream of output, line after line after line, going back to the server, and we just prefix it with out, and then some text. So you could imagine implementing that in a shell script in about 5 minutes, right? It's really, really simple. If you want to implement this protocol over a serial console, you could do that really easily. If we want to do it over WebSockets, it's also pretty straightforward. So this repeats until finally we are at the end. So we send a little message that says end, the process shuts down, and then we go through the final stage of the loop, save the file name of the hash. So this actually is sent out of band, and the reason for that is simple. We can shove all the stuff over WebSockets. It's technically possible, but it's not a good idea. So the WebSocket server then would be sitting, getting maybe 80 gigabytes for a very large job, and it would have to accumulate that somewhere on disk in memory. So we send that out of band separately, and we don't have to worry then from the server side about dealing with a lot of this information. Could be your fancy S3 buckets or some local equivalent of that where you can share it across multiple nodes. And finally, we've done our job. All of these things are uploaded. So we say halt, and we go back to the beginning of our loop, waiting for more requests. So back up to the top, out of the blue bit. Okay. That looks suspiciously small. There we go. Great. So that's how the agent and the server communicates. What does the server actually send us when we get a job? So if anyone's ever looked at a webhook from GitHub or another forge, there's an awful lot of information in it, and we need something short and sweet. All it's got to do is uniquely identify the job, and it's got to tell us where to fetch the data from, and what specific commit, if it's a Git or SVN repo we want. So I don't know if that's readable down the back. Let's make it a little. No, we can't make it any bigger. So we've got 5 fields. I'll start at the bottom. The URL we want to fetch, so that's like http github.foo.com. We have a specific ref, which for Git is the standard SHA-256 hash. We have a job ID, which is some form of UUID, and then we have a couple of other fields. So from a security perspective, we are being sent untrusted data from outside our system that says, please go and fetch this URL. And anyone who's worked on web apps will know the very first thing you try as a pen tester is, what happens if I don't send a URL? What happens if I send alert JavaScript stuff or Bobby drop tables, any sort of malicious code? So we can't trust this. We can't trust the organization name. So what we do is we just take the text you send and we SHA-256 hash it. And after that, we know that it's this length, which is useful later on for constructing paths, and we know it's text. So that's a really nice, simple way of doing that. And we use this both for the cache and the organization name. Okay, so the cache is just a directory on disk where we locate stuff, but we don't want to pass in untrusted text to the commands that will create files. So we hash it, and then we know that they may have sent us garbage, but at least it'll be the same garbage every time. So hashes for user-supplied untrusted data, and for file system paths, then they are opaque. So if you leak that path, no one can take the hash and work out what repo or organization it's from, and it's also length safe. You can't exhaust the file system by trying to run out of the max file path. And it also happens it's ideal for ZFS snapshots, which we'll come back to later. So part of the protocol here is we want to be able to validate stuff. So we want a protocol, an agreement between the server and the agent that says, if you send this data, I will do these things. And we do this with JSON schema. There's a library that's commonly used in FreeBSD called libucl. So libucl is a library that provides, among other things, the UCL config format, which we'll see in a couple of slides. It provides JSON, YAML, and UCL conversion, and also schema validation. So it's pretty cool. And it's screamingly fast, written in C, and this is a simple example of the sort of stuff you can do. So when the job is sent from the server to the agent over WebSockets, we can see that if it's valid, it has to be of a type object. This word here is required, and we've got a bunch of fields, ID, cache, org, ref, URL, the same fields we saw on the previous slide. And these have to have properties. ID is a type string, the same for cache, org, ref, URL, and command. In later versions of the JSON schema, we can apply constraints like the string has to be this long, it has to match the following pattern like a regex, and we can be much more constrained about that. But at least for version 1 for this, we can just say we've sent an object and it has these keys and only these keys. Okay, and that's great. Once we have a newer version of JSON schema and in libucl, we can actually say, right, this ID, not only is it a string, but it's whatever that is, 60 characters maybe, and they have to be 0 to 9 and A to F. So that allows us a lot of flexibility in being sure that what being sent is correct and useful. So the agent has got access to ZFS. One of the really nice things about ZFS is we have delegated permissions. So you don't have to run as root. We can say the user that does the manipulation of the ZFS file systems will start somewhere here, further down the file system, and it can run as the CI user, and that's fantastic. So it's one less thing we need to do as root. We're going to fetch the repo, or maybe it's a tarball, and then we're going to construct a path. So CI or Zen, something nice and short at the beginning. That's one ZFS data set. That's our top level one. Then we'll have an organization, but it'll be SHA-256. So we know that's, whatever it was, 60 characters long on the file system, another data set. And then finally one specifically for the repo that we've cloned, SHA-256 again. So we know the length of the path, and at each of these points here we can say how much space storage is this organization using? It's everything under that. How much is this specific repo using? It's everything under that. Now, I don't know if everyone knows a lot about Git, but Git fetches a bunch of objects and then expands that out to files on disk. But you don't need to do the last step. So you can fetch the objects, which is from a security perspective pretty nice. It's called a bare repo. We're not executing any commands. And then you can introspect that walking down from the ref that we've been given and walk through the file system that Git actually knows about and say, what's in this file system here? What is that file there? Without actually creating on disk. And that's another way we avoid leaking untrusted user behavior into our program. So fetch the repo last week, and Mark's been busy, so there's another 1,000 commits in there. Then we refetch that repo, and now the bare repo contains new entries, and we can snapshot with ZFS after each of these commit fetches, peek inside the repo to find the UCL config file, and work out what we need to do. We've got one more piece in here. So at each of these points here, the ID of the tip of the Git repo that we want to check out is actually a separate ZFS snapshot. So it's super space efficient. And for each job that we have, we can clone that repo at that commit and then mount that into our jail where we do the build from. So it's really space efficient. And at the end, we destroy the clone, the space is freed, and then we fetch again to fetch the next job, add a little bit more to the Git repo, do another snapshot, clone it, and repeat. So UCL configs. The config file is quite large now, and for me, this is one of the pieces that's still in flux. I'm still not sure I've got the right shape, the right structure, the right keys, and so what we have here is the minimal set. We have an image that we want to build from, so FreeBSD latest, here's what I have, but you could have a Linux jail, you might have a specific release, you might even have a custom file system that your organization uses always as its baseline for builds with the right compilers, the right tool set. We have a bunch of tags. So this is the tags that are required to build this particular fork. So we can only build on FreeBSD here, only on ARM64. We've got some arbitrary flag called CI equals true, so we can have Boolean flags. And we have another one where it's just flag is on, and if it's there without an equals, it must be true as well. So these are sent in the beginning at registration, and we'll actually see this later on. So the agent registers itself, and then also says, here's the tags I need for this build. We may have a programming language. One of the things I would like to do is make the CI as sort of intuitive as possible. So ideally, you should install the agent in the server and be able to run an arbitrary build, and for it, without even a config file. And it should say, okay, you've got a make thing here. I'll try GNU make or FreeBSD make, bmake, depending on the system. If it's an Elixir program, there will be a mix.exs, so I'll try that. That's about making the onboarding as simple as possible. For pretty much any Git repo of any size, you will have branches that you want to do CI on and branches that you don't. So we have a very boring little format here with a glob that says, okay, merges and pulls are fine, main is fine, but if you've got a WIP branch, work in progress, let's just ignore that. Part of the config also is environment variables that we want to set. So here again, a pretty basic JSON structure. It's just an object with key value pairs in it, the environment variable name, and the value that it has. And the second part of our UCL config, this is where I kind of had to squash everything up to fit on sides. We have a pipeline, it's an array. We have 1, 2, 3 tasks in here. So from the CI service point of view, that's 3 separate invocations of the agent. And the first one is a setup task. That's just a name, and we need to fetch some dependencies and then compile them. The next task, it's an array, so we have to finish this task before we can proceed to the next one. It's a build. We've got some environment variables and some tasks again, and this one produces some artifacts. It produces a zip file. So from the agent's perspective, it knows if there's artifacts, I get to the end of the job, I'm going to have to pick them up and upload them. And finally, for the deploy step, we have something that looks exactly like env, but it's secrets. And the same thing here, a key value pair and this long base, whatever it is, hash. Now, when I initially did this, I thought, okay, secrets, I'm going to have to use public key cryptography, and that'll be difficult. And I started pulling my hair out. And Lou Vaillant from the Monocipher project said, you don't need to do that. You can use the symmetric keys, but just never tell the server what the symmetric key is. And I thought, well, that's just genius. So that's great. So pipeline tasks we've covered. They can be arrays or objects. This one here is all arrays, so they're processed in sequence. If you wanted to build, for example, on 4 architectures, then you would have an object, and those could proceed in parallel. Okay, so that's how we do pipeline serial sequential tasks or in parallel. Secrets are encrypted symmetric blobs. We just never tell the server about the key, so there's no disclosure possible because it can't leak what it doesn't have. That does mean the agent has the half of the symmetric key, but it's always going to have that because it has to decrypt the secrets to use it. Okay, so the server never has the key, only the agent has it. So, agent ZFS jails. This is the complicated bit. So we have a template that has our operating system that we want to use to build in. We could potentially do this in Beehive, I guess, as well, but I've not looked at that. So we're just using a jail at the moment. It's just a directory on disk. We have that as a ZFS dataset. It's a template, it's pristine, and then we clone it. So now we have a writable copy, and we mount it, which is where our jail will be instantiated, okay? The next thing we do is we take the sources snapshot, the Git repo that we previously cloned, and we mount that inside the jail in the expected place. And finally, we're ready to make a jail. And then we just do the normal thing. We read the, we read the lists of tasks that we need to do. We set up the environment variables when we create the jail, and we just push them in one by one. Do the build. We're ready. The command is finished. Okay, do the next task. Okay, we've done all the tasks, and then finally, we can fetch the artifacts and move them out. So once we've done that, we've uploaded the artifacts, we can dispose of the jail, poof, all the processes are gone, and then we just destroy the clones. We don't need them anymore. So cleanup is super easy, everything rolls back, and we can go through this loop again. We start off with our template, clone the pristine snapshot, mount it for jailing, and we know every single time it's going to be perfect, it's going to be clean, it's going to have the right tools in it. So the dirty C bits. Part of me for this project was scratching an itch. I don't do much C. FreeBSD is written in C. I should learn some C. And so I started off playing with I made a list of the things that were most difficult. And the most difficult part for me was KQ for handling events. So the very first piece of this was just make a program and capture a standard in and standard out. And then the next version of it, the next iteration was now send that standard and standard out over a Unix socket. So what I wanted to have was a jail with a Unix socket sort of hanging out, and then a secure process on the outside that would just read from that. And I kept iterating on that, but the first bit was KQ. The next bit then was WebSocket stuff, and I looked at a couple of projects for that, and it turns out that curl is adding WebSocket support. It started about a year and a half ago. It's got a really nice API. Curl's available everywhere. It's going to be a great thing to use, and I really enjoyed that. It's not yet listed as production ready, although I've had it on good advice that it totally is. We just need to polish up some man pages and stuff like that. And as soon as that's done, the libcurl library and FreeBSD ports will have this functionality in it. Today you don't. You have to compile it from source with an option enabled. So curl provides us the WebSocket connection, and that's where we do registering capabilities and waiting for jobs. Finally, after that, we then init our Lua state and load plugins. We'll talk about that shortly. Then we fetch our sources. We look inside the sources and find this libucl config file. And then we add a Unix domain socket. And now we're ready to fork. We have a trusted process on the outside that has a network connection. And we have a process on the inside which will jail itself and then start sending the output, the standard error, standard out, back over the domain socket into the process that has the network connection, which then is sent off to our server. And then at the end of that, we loop again, uploading the artifacts and then some tedious cleanup. So that's words. What does it look like? It looks like this. So we'll look at the detail in a second, but the main thing you can see here is do this, and if it fails, clean up. Do this, if it fails, clean up, etc. So most of this here, this is our happy path. That's the bit which I had to program. Here's the KQ loop in the middle. Here's the jail happening over here, and all the rest is just cleaning up. So a lot of cleanup. Let's look at that. SVG. Here we go. Yeah. So if I make this, if I embiggen this, it will become readable. Okay. Can we read that yet? I can't read it without glasses, so don't quote me on exactly what it says. So at the beginning, the agent has to decide, am I running in the classical client-server arrangement, or am I just running like a dev mode where it's a local command line tool, and as a developer, I want to be able to run the CI jobs locally before I commit them to Git, before I push them up for public shaming from my colleagues and watch it fail in production. That is a feature I personally would love to have. Yeah, I've always wanted that. Once we do that, if we're in server mode, we're waiting for a configuration. This is the job server saying, here's some work for us to do. Here we go. And once we receive the blob of JSON, we validate it using our libucl schema validation. Are we being sent stuff that's correct? If it is, then we're okay to load it. And we go through down retrieving our source code, which we talked about earlier. So let's keep going our happy path. Oh yeah, here we go. We need to make that a little smaller, don't we? Cool. Yeah, so here we've got our config, and we're now ready to make our Unix socket and do some fork magic. And so here's our fork happening here. We're going to look at this in two parts. Whoops. So we fork our process, and the parent process will close its file descriptors and just wait for the child to send data. And once that's done, once it's got data, it initializes its connection for sending the job results back. And then we just go through this little loop here, the KQ loop. So what have we got we want to pick up here? Yeah, there's two things happening here that's of interest. We're in the parent right now. So if the child is closed, then we should end the job and see if there's any artifacts for us to send. If the child hasn't closed, maybe it's not sending any messages. So we need to tell the server that stuff is still happening. And WebSocket protocol has an inbuilt ping where it just sends a message back from each side so that we know the connection is active. And we do that by default, I think every 10 seconds, I forget, it doesn't really matter, but we send a message back so that the server knows this job is still active. We need that from the server side because we don't want to allow your crypto miner to run indefinitely. So we want to know that it's doing stuff and sending data back. And if it's not, then we're going to kill it with fire, okay? So if all of those things are happening, then we're going to be getting chunk data coming in from the child. We're going to scoop them up and push them out over WebSockets back to the server. And one of the tricky things with this is, where does the line end? How much data are we being sent? We don't know, and there's a little bit of mechanics underneath to try and make sure that we send valid lines so that the web server can display them in orderly fashion. But also we have to assume untrusted input. Maybe someone will try sending us a 1,000,000-line log thing looking for a buffer overflow. So let's look now at the child. So we've forked. One half is handling the network connections to the outside world. And because this is FreeBSD, this child process where we're going to run untrusted code, unfortunately, is still root. So it's not great, but it is what it is. If we want to do the jails, we've got to use the root. So we enter the child process. There's some setup to do. We close our file descriptors so that the data from standard in, standard out will actually go through our Unix WebSocket. And we create the jail. And this gets a little messy here on the screen here. Here we go. We create the jail. And the main thing on FreeBSD with jails is when you create the jail, the process that is asking this request becomes the jail. It jails itself, which is a bit weird. And that's why we've got this fork earlier. The fork is sitting outside. It's not the same process. It's handling the network connections, and we're now on the jail on the inside. The cool thing is, what's not displayed on this diagram, is that we load our Lua plugins first. So we're now inside the jail, and we still have all our Lua plugins that were loaded. They're not loaded from the Git repo. They're loaded from our trusted external environment, and we can do useful stuff with Lua before we finally hand it over to whatever command the user or the job has requested. We do a little loop, sending the standard IO data out over our Unix socket, which is picked up just off the screen. And then finally, the command in the jail finishes, or it gets timed out and burned with fire. And then we finish here, and then we go down to exit. So, and if you're wondering how this is done with a mermaid diagram, and mermaid is awesome because the config is plain text, so you can store it in the Git repo and you can version it. And I've actually got two versions of this. I've got one version for one client implementation and another version for this one. So, we've done our KQ loop. We've done our jail loop. Implementations. Note implementations plural. So we're not finished yet, but we still have more than one implementation. The web server side, the web sockets, the UI is written in Phoenix, which is a wonderful web framework written in a language called Elixir. It's a functional, high-level language, so that's great for doing that sort of thing, but it's not really great for doing things like becoming root and talking to jails. So when we're testing this, we use WebSocket, which is a wonderful command line tool. It provides a bit like a shell for WebSockets. You can type the stuff you want to send to the client in, and you can receive the messages back. So that's great just for testing on your laptop. We have two clients for spec testing. One is, again, an Elixir, the same high-level language. It's awesome because it runs on any operating system, including Windows. So I use this for checking that I haven't done too much FreeBSD specific stuff. And then I have the C version, which is the native version with jail support, and that helps keep us honest. So the Lua overview. Lua is a lightweight MIT licensed language. It's quick to learn the basics. It's pretty complicated if you want to keep going. People have done amazing things in it. It's designed for embedding and C integration. For example, there's no directory function. So you can open a file, you can read a file, but if you want to find out what's in the file system, you have to write some C, which is okay. We have people who can do that. It's stack-based, and what that means is the entire state of our Lua VM is a little magical blob, and we can pass it around in variables. If we fork, we can hand that state over to the other process, and everything keeps going. Lua's not a big language, 24 lines of code, and it's about 240 kilobytes, and it's damn fast. For me, as a functional programming language user, it's much faster. It's great. And it's everywhere in FreeBSD. Bootloader, we have a Flua scripting library in base. We have hashing, jails, POSIX support, and UCL config and schema obviously as well. And not in base, but in one of my patches, we have HTTP support with fetch. It's in the package tool, it's in ZFS channels, and it's in our cloud init implementation called NewAge init. So there's plenty of it around, and it's reasonable to expect FreeBSD developers to be comfortable with that. So, a couple of slides on adding Lua to base. So there's a library called libfetch in base, which talks HTTP. We want to use it. So obviously there's going to be a little bit of C to handle that, which is not really interesting. We have to register the two functions we want to use. So we've got a get URL one and a parse URL, and they're just attaching a string name to the function, the C function that's going to be called. And then we provide a Lua implementation of that and push it back onto the stack so that the next Lua command can pull this up and use it. So that's really all there is to it. You write your C code, you write two more functions, and now you can use it in Lua. And what does that look like for fetching it from Lua? We pass in the module we want to use, and then it's now available under this F namespace. We parse the URL, and this obviously is false because the backslashes should be forward slashes. So it says nil. Yeah, that's not a valid URL. And then we can parse the URL into structure and have key value pairs of the content we want. So it's really nice to use. And then finally, we can use this new URL that we've fetched to actually fetch data into a file. So Lua is really easy to implement, and if I can do it, you all can do it. Okay? So Lua plugins. We want to implement as much as possible in Lua because it's easy to write, it's portable, and most importantly, unlike shell scripts, it's really, really testable, and that's really important. So within the jail or on the wrapper, because there's no dir function in Lua, we load our plugins in the C stage, but then we use Lua to call the init script, which is in Lua, and in future we can do sandboxing of the actual plugin init. So everything takes and returns a Lua state, which is just a stack, and this state is available in both forks. So we load our plugins at the beginning, and they're available on the left, the parent, and on the right, in the child. So the plugins are what we use to do the ZFS manipulation, and that is what I will also use for doing firewall rule changes as well. And the idea is that anybody can add their Lua modules to it to extend the functionality. So plugin implementations, a couple of lines of C again, it's the same as before. There's a state, there's a function, and we just, what do we do here? Oh yeah, we allocate some memory and then load the script in, and then I have my glasses on, but if I did have somewhere here, there's a do Lua, maybe it's on the next slide. Then we execute the Lua script. Yeah, here we go. So here we go, Lua do file. So using Lua from C is pretty easy. You just either load the script from the file system, or you can have it embedded in the C code, and it gets executed. And at the end of the execution, you check whether it worked, and you have a new Lua state that you can pass around to the next execution in your program. So key point, plugins are loaded from the host file system. That's our quasi-trusted environment, but they're executed inside the jail in the untrusted world. So we have the best of both worlds. We know what we're loading. The only stuff that executes inside the jail then is the stuff that was in the repo and the stuff we put in there. And for registration and notification, when I did this, I was thinking, how can you combine these things? This feels really awkward. There must be a way to do it. And I realized that I can just have each Lua function in its init stage return a list of events that it's interested in subscribing to, and we use this as an event bus. The only constraint is that the left fork and the right fork can't communicate. So the state machine is only accessible inside each Lua environment. And a pretty short hello world. So here we define a couple of functions, and here in the init phase we say subscribe the world and the world and the registered functions. So any other Lua function that wants to call this can just do that. So here we have a file system function. It's got some mounts and unmounts, and it calls the hello event here. So any Lua function can invoke another Lua module, and that's how all the internal stuff is implemented. So on the UI and UX side, we're not quite at package install and ready to go, and we're just going to mainly look at the UX side, the Unix side, because it's more interesting for us, but the website is very, very pretty, so we're going to finish on that. So we've got two terminals, one running WebSocket and an agent in the other. We can just type in a fake JSON blob, which is this piece down the bottom, and this is what we see from the client side. It sends us registration information, and then we send the job request. Where's the mouse? There we go. And here we can see an out message coming back from the client, hello world, and then saving a hash out to the server, and then finally halt. So that's our agent loop being implemented. Okay, client agent. There we go, that should be a bit easier to see. So this is now the agent itself doing the same code. We can see at the top, it's listing a bit of information about its plugins. This is the registration information it's going to send, and these are the environment variables that are available inside the program. And we've got lovely tracing there in blue and some general info over in green. And here we can see our Lua init system starting up and publishing an event. That's how file systems are loaded. That's how you can sort of chain things together. Go back. The WebSocket messages are interesting, but we won't go into them in great detail. One of the nice things about curl is fantastic debugging, lots and lots of it. And by setting an extra environment variable, we see the internal messages that are sent over WebSocket. So it's a delight to implement because it really is easy to see what's going. So here I implemented a very complex CI build. It runs ping with a count of 3, which is nice because then you have this nice, you know that you're going to get an event every second. And in here we can see the first line coming back from ping, the encryption and sending it over WebSockets, the flush, all that's provided by libcurl. It's tremendous. And then we're sending a liveness ping because we didn't get a message from ping in time, so it's the responsibility of the client to inform the server that we're still going. Here's another ping down the bottom, and finally, it's the end of the payload if we go further down. So, whoops. And this will look familiar to anyone who's used CI. And Michael did an amazing bit of work here. I really love what he's done. We've got active jobs in green. We've got failed and timed out jobs up here, and buttons to click on to delete jobs or to rerun them. This is a little bit harder to see. Do I have? No, I don't. Let's see if I can get this. One of the things we get with CI is you get a lot of information, piles and piles and piles of it. And so what we have is this little way to collapse a field. So when we're viewing it, we can either expand the whole job or just look at the last couple of lines here. And it's a really nice way to see the jobs that are running. Whoops, I've done it again. And then we've got a bunch of agents here. And the agents are pretty simple. They register, they're either running or they're not. And we can choose to delete them, which means the server will refuse to talk to them, or we can stop them, and because they're running under daemon, they'll just restart themselves and clean up their state. So big thanks. Kyle Evans and Mark, you're my Lua heroes. Thank you very much. I wouldn't have started this if you hadn't made it look so easy. Faraz for his C guidance, libcurl, Badger, and the community curl committee for the WebSocket support. Lou Vaillant for the monocipher and the occasional emails explaining crypto stuff. LogC, which was the pretty logs in C. LibUCL from FreeBSD from Blossavod for config and schema. FreeBSD Jails working group for guidance and moral support. Michael for the amazing web UI. Joy for the web and Elixir client, and anyone who works on FreeBSD, Elixir, and Phoenix, because I wouldn't have done this without you. Help wanted, actual use cases, not just the stuff that I have. Contributors and hackers. I think by the end of the year I should have a release that is enough for other people to use and iterate on. And I'd like more Lua accessible APIs, libpf Lua, Lua PF, and libzfs mainly. It would be nice not to shell out to commands all the time. And in closing, thanks for all amazing libraries. LibUCL for the data format and validation, KQ for capturing the jails, Lua for extension, WebSockets again, and in the future, a cross-platform dream, and open source once we're self-hosting, when we can build and compile our own CI and test it, both for BSD and other organizations. Okay, thank you. I know. Any questions?
Thanks. So what is your actual use case? I still have this big...
Oh, maybe we should turn the microphone off, yeah. The butler did it. I don't want any more butlers in my life. That's Jenkins and Java. When this all started, I kept having to upgrade Jenkins because of security vulnerabilities, and I don't want that anymore. Personally, I build software where I want to distribute a package out to FreeBSD servers and then run them. And doing that with Ansible is fine, but I wanted something that was a little more, what's the word I'm looking for here? That can be automated in a controlled fashion. So Ansible is a separate thing you run and trigger, but I wanted something that would say, do the job. If it works, send it out to 5 servers. If they work, go on to the next 5. And I wanted to be able to express that in this graph format rather than an Ansible script that's more and more shell scripting. Yeah.
And why all the effort for privilege separation? And frequently you mentioned untrusted code. So where does the untrusted code come from? In my mental image of a CI infrastructure, that's a bunch of servers that control node.
Yeah, that's a great, yeah. Yeah, so the more organizations I see, the less convinced I am that they should trust each other. But part of this motivation was, as a FreeBSD user and committer, as a port user, I would like to be able to have someone submit a port for me to run that build to see whether, as a committer, whether the maintainer's port compiles, does it build, does it return errors, and from that perspective, it's untrusted. They may be a maintainer, but they might have pulled down XC with unexpected vulnerabilities from our favorite foreign governments, and we can't trust that. So, yeah, trust no one. Thank you very much. Oh yeah, thank you. Oh.
the enhanced libc strings functions. Take it away.
Yes, thank you, and welcome to our talk. Today, we're going to tell you a little bit about how to optimize libc string functions with SIMD techniques. And so there are lots of things you can do with strings in libc. You can copy strings, you can find the string length, you can find characters, you can compare strings for equality, you can find substrings and other strings, you can split strings at delimiters or match against sets of characters. And these functions, they look like they're very different, but at the core, they just boil down to a bunch of very simple operations. So for copying strings, you first have to read a string, and then you write it to some other memory location. For finding the string length, you first have to read the string, and then you compare each character with a null byte to find the end of the string. For finding a character, of course, you read the string, and then you compare each character with the character you're looking for. And yada yada for the other ones. For comparing strings, you read the string, and then you compare each character with another one to see if they're equal. And splitting at the limiter is a bit more complicated, and finding substrings is very complicated, so we won't really cover this in this talk, but more on that later. And about these operations, they are all very simple to implement. If you read a string, you read the string character by character until you find the end of the string, and then you're done. So that's one load, one comparison, one conditional branch per character. Writing is similar. Write each character individually until the string's done, and then you're done with it. Comparing is similar. Compare each character individually, and you have one conditional branch per comparison. All of these operations have in common that they're very slow, because we proceed character by character. We have a data dependency on every conditional branch, and it's just a nightmare. And usually string functions are not that fast for this reason. So what does this tell us about strings? Well, the conclusion is strings are terrible. Nobody likes strings. And yet, strings are everywhere, and we can't really get rid of them. So what can we do about this? Well, we could try to tell people to program without strings. This is not something people want to hear, and it's not something programmers want to do. Strings are nice because they are kind of high level and user-friendly, and in many applications, they're just something you want to work with. On the other hand, on the other side, there's billions of lines of code that already does string processing, and we can't exactly tell people to ditch all this code and re-engineer it with other code. So if we want to make an impact, we have to accelerate existing code instead of telling people to rewrite their code with some other framework. We could use some special machine instructions that implement string functions in a single instruction. For example, x86 has machine instructions to implement string copy and not mem copy, mem set, maybe string length, maybe some others. But this is kind of problematic because these instructions vary in their performance quite significantly depending on which model CPU you have. Sometimes they're very fast, sometimes they're very slow. And the best way to use them, if you want to do it at all, is to have a big pile of code around them that kind of decides if it's appropriate to use the special purpose instruction or not, and only uses it in the right case. And this is very complicated. So what is left is to dig very deep in our box of tricks and come up with some smart ideas. And the idea is to use SIMD. I think many of you have heard of SIMD before. SIMD stands for single instruction multiple data, and is a feature most CPUs these days have. SIMD means you have special registers in your CPU that don't hold a single datum, but rather a vector of data. So for example, a SIMD register in your CPU might hold 16 bytes of data, and the CPU can process these bytes as 16 individual bytes, or 2 shorts of 2 bytes each, or 4 single precision integers of 4 bytes each, or 1 double of 8 bytes each. 2 doubles of 8 bytes each. And usually you can do the same operation on all the integers at once. So in theory, if we have a vector of 16 bytes and we process them byte-wise, we could reach 16 times the performance of a scalar code, because each of the SIMD instruction takes the same time usually as the scalar conventional instruction of the same type, but it processes a lot more data at the same time. So theoretically, we can think of a speedup of up to 60. In practice, it's a little bit less, because using these SIMD techniques will incur additional overhead in other ways, and the algorithms used are usually more complicated, but we can generally expect a significant speedup of a factor of maybe 2 to 10, depending on the function. We'll see some performance figures later in the talk. So to illustrate the idea of SIMD, here's a simple operation. We have 2 arrays, and we want to sum them into another array. With scalar instruction, we would have to use a bunch of individual additions, and each of these green boxes is one add instruction that takes like a cycle. And with SIMD, we have a vectorized add instruction that takes a cycle too, but we only need 1 instead of 4. So that's a speed up by a factor of 4 in theory. Typical SIMD operations include arithmetic, both for integer and floating point. We have a bunch of bitwise logic instructions. We have data transfer instructions. We have instructions to generate masks from SIMD registers. We have comparison instructions. For example, if you do a comparison on a SIMD register, that means that each element is compared with the corresponding element from another register, and you get a result that is either all 0 or all 1 bits, depending on the result of the comparison. And then you can use this result as a mask to mask out elements, or you can transfer it into a scalar register to process further with scalar instructions or whatever. For our work, we'll mostly need very basic logic instructions like bitwise logic. We need comparison instructions, and sometimes we need some special instructions, but it's very simple. And you just need to keep in mind that all of these instructions we use here are vertical. That means that each element of the vector is treated the same way. Many modern SIMD instruction set also provide instructions that are horizontal, in the sense that instead of each element of the vector being operated on the same way, the elements are operated with each other. For example, a typical horizontal instruction is a horizontal sum, where the elements of a vector are summed into one big sum. Horizontal instructions were uncommon in the past, but recent SIMD extensions have more and more of them, and we will cover a few useful ones of them in later parts of the talk that can accelerate text processing. But most of these algorithms we have come up with for this project use horizontal instructions almost exclusively, because that's most of what is available in the most basic tier of SIMD supported on the AMD64 architecture, which is the architecture we've started to implement this on. And we wanted to make sure that SIMD optimizations are available for all AMD64 processors and not just the most recent ones. So we've decided to stick with the most basic extension level possible. So how does this help us with string processing? Basically, the idea is we want to load a bunch of characters into register, then we want to process them all at once, and then eventually it works. So here I have a string that says foo bar bas and then a null byte. And we want to process this string in parallel with SIMD. So for these examples, I use a vector length of 4 bytes, so it's nice and easy to see on the slides. In reality, the vectors will be a lot longer, but you can see the general principle of operation. So we'll read 4 bytes. OK, that's good. We see there's no null terminator. We can continue. We read another 4 bytes. No null terminator either. We can continue. And then we read another 4 bytes, and we've just overshot the string. So that's bad, and at this point, our program might have just crashed. So this whole idea of using SIMD to process strings in parallel seems like it needs some more thought, and we'll have to think about it some more. So this is not nice, and it seems like with null terminated strings, we cannot really avoid this problem, because until we've seen the null terminator, we don't know where it is. And if we don't know where it is, we don't know how far we are allowed to read. So can we do any better than reading character by character after all? Turns out, yes, we can. String bounds are a high-level concept imposed on us by a programming language. They are a fiction. They are not real. And we have to overcome them. We have to let go of the idea that objects end where the program says they end, and think about what the machine can actually do. So the idea is a computer doesn't know what an array is. A computer just has memory, and in some addresses of our address space there is memory, and in other addresses there is not. And as long as we only access memory where there is memory, the CPU is usually fine with that. So if we don't go too far out of bounds and make sure that we stick within memory that is guaranteed to be present, then it'll be fine. Really. Static analysis tools don't really like this, but that's OK. We've patched them so they don't complain. And we can't really do this in C, because C has a lot of rules about this, and C actually wants us to obey these fictional rules. You can turn this off with some special flags like no strict aliasing and so on. But for this project, we've decided to implement all this code in assembly, so we have exact control over what memory accesses are happening and what not, and the C compiler is not allowed to mess with our code and do weird things. So how far can we go? The idea is memory is organized in pages. So each page is 4 kilobytes, usually. Some architectures have different page sizes. The code needs to be adapted in this case, maybe. And the granularity according to which memory is accessible or not is a page on conventional architectures. A page is either completely accessible or not accessible at all. And unless you have a fancy architecture like one of the architectures used by the Cherry project with capability-based access, that's really all there is. And as long as you make sure that you don't stray off into other pages, accesses usually work. And the idea here is that if we have a string that is, of which at least 1 byte is on a page, then it's fine to access the whole page. Because the C programming language guarantees us that the string is accessible up until the null byte, and the hardware guarantees us that if the null byte is on some page, then the rest of the page is accessible too. And the most basic way to make use of this is to just do aligned memory accesses that intersect the string we process, because an aligned access never crosses a page boundary. The page size is a multiple of the alignment of all the data types we have on a CPU. So if we do not cross an alignment boundary, that means our access is confined entirely within 1 page, and if it intersects the string, it is fine to do. So we just have to program our code such that each access intersects the string in some way, and that is probably easy to achieve. So here I've drawn the same string again, but this time with alignment boundaries drawn in. So you could think of these big black strokes as being page boundaries or alignment boundaries in some way. And if we do accesses that intersect the string and don't cross these boundaries, then the access will be fine and everything will work. So what we do is when we start processing the string, we round down the pointer to the previous alignment boundary and think that the string kind of looks like this. So before it, we have some memory with undefined contents, and after that, we have some undefined contents too. And we just have to ignore these bytes and make sure the algorithm works despite them being there. So we start to read from the previous alignment boundary. We read the start of the string with some junk before. We have to mask that out. That's fine. That's easy to do. We find there's no null byte, so we read the next chunk. And then we read the third chunk, and we see a null byte. We know that the string doesn't extend anymore, so our code is done. At each part of this operation, we know that because we have not seen a null byte, the string extends for at least 1 more byte. And this gives us license to read the next chunk of the string. This works fine for reading strings, but we do have some special, some other applications that are more tricky. For example, writing strings can't really use this approach. While it's fine to slightly overread an array in this manner, it is not fine to overwrite an array. And that's even if we write back the same bytes we read. That is because in a multi-threaded program, there might be another object right next to our string that is owned by another thread and is concurrently accessed. And even if we write back the same data we just read, another thread might have intermediately modified this data, and this update may get lost. So we must be very careful not to write into data that doesn't belong to us. So the approach here is that we write the string in possibly unaligned chunks of memory, and then to cover the last few bytes, we just do an overlapping write. We just write a bunch of bytes twice, and that's usually fine. Some microarchitectures do such an overlapping write with a bit of a penalty, but you can usually work around this so it doesn't happen. For example, if you do the last write ahead of time and then start from the beginning, the last write has retired by the time we reach the end of the string, and the CPU doesn't even notice that it's an overlapping write. This, of course, is only possible if you have a CPU that permits us to do unaligned writes, which is most CPUs these days. There are some exceptions like RISC-V, where it's not guaranteed by the architecture that unaligned memory access is possible. On such architectures, string copy is a bit more expensive, and you'll have to find tricks to make sure that all writes are aligned. It's a bit more complicated, but most architectures are not affected. So here's what that looks like. You have a buffer in memory, and we want to write the same string into the buffer that we just read. So we write 4 bytes, we write another 4 bytes, and then for the last 2 bytes, we just cover the end and do another write that kind of writes BAZ and then a null byte, covers a bit of the rest, and we have two writes. So that's writing, reading, writing. Comparing against a single character is very simple. That doesn't need a special technique. But one function that is very hard to do is comparing strings, so string comp or memcomp. Memcomp is a bit easier. The problem with string comp is that if you read one string with the aligned approach, then the other string may have a different relative alignment than the first string. So if you read two aligned chunks from two strings, they may represent different sections of the string, and you can't directly compare them. On some SIMD architectures, on some SIMD instruction set extensions, you have instructions to do byte shifts on SIMD registers, so you can align the two strings after the fact. But unfortunately, no such instruction exists for SSE2. And on other architectures, it's actually very expensive to do this. So the idea is we do aligned reads to check for null bytes, and then we do unaligned reads to actually compare the two strings. Because the unaligned reads allow us to have the same chunks of both strings to compare, and the aligned reads allow us to check for null bytes without crossing into unmapped storage. And this is what it looks like. So for example, here we have two strings. They are identical because that allows us to demonstrate the algorithm to the end. You can think about what it looks like when the strings are not identical and how to deal with that. And in this case, we start by checking for the end of the string. Here, yellow means that I've successfully checked that the string does not end here, but I haven't checked if the two parts of the string are equal. So we start by checking if the two prefixes are equal, and that if the string ends in the prefixes, and that gives us license to cross into the next chunk. So next we can compare the prefixes, and that says, okay, now we know that the two prefixes are equal. Technically speaking, we would have now successfully compared 4 bytes, but for the sake of the algorithm, we assume that we have only compared the shortest joint prefix that is shared by the two strings that we've already validated. And it will become clear that this makes more sense in this algorithm. So we carry on by checking if there's a null terminator in the second string that goes ahead a little bit. And then we check the first and the second string for equality in this chunk. And that also covers the null byte check. Because we know that the second string has not ended yet, we know that if the first string is equal to the second string in this chunk, it will not have a null byte, because the second string didn't have one, and if it's equal to the first one doesn't have one either. If the check fails, we know we need to manually check for null byte, but this approach allows us to mostly ignore null byte checks for the first string. So we only have to do two checks per chunk, one to check if there's null byte, and one to check for equality instead of a second null byte check. Saves a bit of time. So we carry on, we do another check for the end of the string. We see, okay, the end of the string comes, so we have to terminate the algorithm. We do a final comparison for equality, and now everything's fine, and the strings have been successfully compared. It's a bit more complicated if the string ends within the prefix. So if the string ends within the first chunk, we cannot assume that it's safe to overread the first chunk. So we can't just compare the two prefixes, because that would cross into the gray area and that could induce a crash. Some other implementations do a check if there's a page boundary, and if there's a page boundary, then it does a character by character check to not cross into the page boundary. What we do is we copy the string head to the stack, because we know the stack is always mapped. It's always safe to access the stack. And when we copy the head to the stack, we can safely access beyond the head, because we know there's mapped storage afterwards. So we copy the offending string onto the stack, then we do the comparison, and everything's fine. So this is how comparing strings works. Another function that is a bit challenging to do is set matching. So set matching, like strus-cspan and strusspan, compares a string against a set of characters and tells us what is the longest prefix of the string that does or does not occur in the set. So for strus-cspan, we are looking for the longest prefix of the string that does not, whose characters do not occur in the set. For example, here we are looking for the longest prefix that does not have a space, a tab, or a new line. This is very commonly used for string tokenization. If you've used functions like strusep or strupbreak before, they all boil down to this primitive. This is a bit complicated to implement, because to to match against a set of characters, we can't really do a vertical operation. We have to compare one character of the string with each character of another string. There is an algorithm to do it with some shuffle operations due to Muya and Langdale, and that one is pretty fast, but maybe we can do better. And in this case, Intel has a kind of crazy instruction called packed compare implicitly terminated string return mask that does all of that in one instruction. So it does set matching, it checks for null terminators, it can also make coffee if you ask nicely. This is the flowchart. So you start with 2 strings. The instruction checks for the end of string. Then it internally compares each character of one string with each character of the other string. Then it aggregates these results according to an aggregate predicate given as immediate. So you can either have equal any, which does the set match. It can do ranges. So you can do like a range of, okay, I want 0 to 9 and A to Z and capital A to capital Z. This allows you to compress large sets into one vector. You can also do equal ordered. This is used for substring search. So you can, technically speaking, implement str with that, though it's a bit slow for this purpose. You can do equal each, which does a straightforward string comparison, though it's not really useful because it's much more expensive than doing it the straightforward way. Then you can do a negation, so you can check for both the complement and the set itself, and it can also deal with the bytes after the null terminator, so it all works out. And then you either get an index, so it can tell you where the first match is, or it generates a mask. And we use the mask case because it's easier to post-process. This instruction, believe it or not, is very slow, so it takes like 10 cycles. But on the other hand, the Langdale-Muya algorithm only takes 9 cycles. Still, this instruction is faster because we can fire in another one every other cycle or something. So we lose on latency, but we win on throughput. So this one is better in Intel. On other architectures, we unfortunately don't have this. ARM SVE has a similar one called Match, but unfortunately, nobody seems to own a processor that supports SVE. So maybe we'll have to revisit this in a number of years. Another function that is a big question mark is str. Str is, so substring search is very complicated. In FreeBSD, we have an excellent implementation from 1996 that uses something called the backwards-forwards string matching algorithm and has all sorts of special cases. It is kind of hard to beat this one, and it is very hard to do so with SIMD. There are a number of papers on fast string matching with SIMD, but unfortunately, these papers are optimized for very long strings. So they have a test case like, look for all instances of the word holy in the Bible. And they're very good at this kind of stuff. But in libc, what do people use string functions for? Well, they're doing things like, does this path contain bin? Does this list of options contain the token we're looking for? And maybe the token is like 5 characters and the list is like 20 characters. So if we have an algorithm that is optimized for searching through the Bible and starts by preparing a giant lookup table to then breeze through the rest of the code, that's not something we need. That's not helpful at all. And it's a bit hard to find material on string matching that is optimized for the case of short needle, short haystack. And a bit of research is needed to make this work, and I haven't really been able to find a satisfying solution. So this is future work in progress. We'll have to revisit this one. Now this was about the theoretical aspects, the ideas of how it works. Gats will tell you a bit more about the implementation details. Now how does this relate to FreeBSD? In 2023, the FreeBSD Foundation contracted me to re-implement all the libc string functions for AMD64. We managed to get through almost all of string.h with some assorted exceptions like str. We widely ignored all the white character stuff because nobody uses that. That may be something for future work. The architectural target was AMD64 baseline, so that what the instruction set all AMD64 processors support. Selected few instructions instead require x86-64v2, which means everything up to SSE 4.2. This includes the PCMP ISTR-M instruction that I mentioned earlier. But this is only for a few instructions and for a few functions. And the code actually does a runtime dispatch. It will check your CPU features and then pick the right implementation depending on what your CPU is capable of. This dispatch is based on the GNU ifunc mechanism, so it's done when the runtime linker initializes your code and only affects the selected only affect startup costs a little bit. I've written a dispatch framework that is nice and fast and doesn't really noticeably affect us. Due to the complaints of a number of project members, we've also implemented a scalar fallback for AMD64. So you can disable this feature and have all scalar code that doesn't use SIMD at all. And that also works. It's also pretty fast, just about half the performance, maybe a third of the SIMD implementation. These features landed with FreeBSD 14.1 release, and they're also in current, so they will also be part of 15. We have decided not to backport this to FreeBSD 13.4 or something. So if you're on FreeBSD 13, I'm sorry. Maybe this is a reason for you to update. This year we have submitted 2 proposals to Google for Google Summer of Code to port this work to 2 new architectures, AH64 and RISC-V64. And both projects were successfully completed, AH64 by Getz, who is with me right now, and RISC-V64 by Strahinja Stanisic, who could unfortunately not attend this conference due to visa issues, but he also did some great work on RISC-V. The current state of the project is that the AH64 port is basically done. We are currently in an acceptance test process where we build all the ports with the modified functions and then check if any of the ports stop building or start building. That would be very concerning, but this is in addition to a comprehensive set of unit tests we've written for this purpose, but unit tests are not the end to all things and they may miss something, so we have decided, due to the importance of string functions, to do this more complicated validation procedure. This is currently work in progress and may take another 2 or 3 weeks, and then we'll be able to land these changes. The RISC-V work is work in progress. Strahinja got a bit sidetracked by university stuff, so we'll look into doing the XPRON in a couple of weeks. It will be a bit more challenging because we don't have super powerful RISC-V hardware, so not exactly sure how to do it, but we'll figure something out. Now, the slide you've all been waiting for, results. This is a benchmark chart. So for each of the functions on this list, I did a micro benchmark that exercises the function with a variety of string lengths. The average string length is 64 bytes in each case. And you have in blue the pre-state, so that means generic C code. In orange, you have scalar implementations. Where you don't see a blue bar, that means that FreeBSD already had a scalar implementation before we started the project, so the generic C code was never executed for AMD64. And in yellow, you see the SSE implementations. For one function, timing safe memcomp, it was not possible to implement it with SSE for various reasons, so we only contributed a scalar implementation. And from these results, you see that the performance improvements have been significant. The average improvement is by a factor of 5.5. And maybe with some future changes, we can improve this number. And now I would like to hand over to Getz, who will introduce us to some details about the port to AH64 and introduce us to some technical details on how this all works.
So I ported Robert's functions to ARM64 this summer as part of Google Summer of Code using ARM NIA ASIMD extension with Strahinja porting it to RISC-V. We already had several functions already in our source tree from ARM optimized routines, but then the question was, can we do better? There was also functions missing, but as at the end of this project, just about all functions are now SIMD optimized. Most common instructions are available across different architectures. ARM64 has similarities like pack compare for equal bytes. So we have CMEC, compare bitwise equal. And then with an arrangement specifier, we can get the same effect. There are also bit scanning instructions and minor variations. So scan for the first existence of null bytes. For example, so quite a little bit of extra fiddling because there's no trailing zero count on ARM64, so we got to reverse the bits and do a count leading zero instead. Also, another nice thing we do to avoid an extra branch in the tail handling of string function is that we induce a fake match in the match mask. This is done using bit test set on x86, and for ARM, there's no equivalent, but instead we just shift 0xf by the appropriate amount to the limit and OR it to insert the fake match. This way we can do the trailing zero count and it will act just as expected. And then there's a point of not stepping into an unmet page and resulting in a seg fault. For this on x86, there is the p-shut-b instruction. It is a part of SSD3, so that would be up to the x86v2, right? But on ARM64, we got the TBL instruction, which does the same and more, which was very nice for these cases. So Robert had to go to using the stack while on ARM64, which is preload the register and then shift into it and load the data, use TBL, and presto. Because there's no type of variable shift for SIMD registers on ARM64. Some instructions require some imagination, especially P1 math B. There's a lot of posts and articles about this online. We also came up with a novel solution for this, but it goes to SIMD registers. It has 128 bits, and we need to go down to 64 to fit it in a general purpose register to do our funny business. We found that shift right narrow, which is this one, is very suitable for this. The only difference is that this fills an entire general purpose register, while the p-move mask byte only uses 16 bits. So for a simple Sterling implementation in x86 on the left and ARM64 on the right, there's a p-move mask b, get it in a GPR, and then just loop back. If a match is found, we just go find where it's no longer 0, because a match is a 1 or an F. While on ARM64, we do a shift right narrow, check is there any zeros, reverse the bits, count using 0, and we're good. There are also notable alternatives to P1 mask B. We used UMaxV, which gives us the largest byte value of a SIMD register. This is better on the case for the long strings, so we would often go and do a shift right narrow in the beginning, and then for when we realize that, okay, this string is quite long, we go using UMaxV. Then we had the novel solution of just preloading a register with 0, 1, 2, 3, 4, 5, and then when you OR it, you're going to get, and then a UMIN B, you're going to get a bunch of Fs, and then 0, 1, 2, 3, 4, 5. You just extract that, and you know the index of your mismatch. And then there's the ones that require a lot of imagination. So the p-copy-stir instruction is not widely available in other architectures. Sadly, we don't have SVE, so I did some work trying to get this working, but I resorted to using a lookup table solution instead, which Robert made for x86 in the beginning. There's also the case for when for stir span and stir c-span, where an empty set creates just a Sterling and a one char set creates a star char null. Future work would be to port the Mula Langley algorithm for ARM64, and we're also getting SV support in the FreeBSD kernel, courtesy of Andy Taylor. And we also were thinking of maybe adding an arch level flag for ARM64, similarly to what we got for x86, for choosing to have the ACMD algorithms or SVE, and then also for AVX2, AVX512, if we get around to writing those. We're also implementing the functions, but they're a bit nasty, and also finding out how to do stir efficiently. And then if anyone has ideas for other parts of the libc or the FreeBSD operating system where we could use other fun SIMD optimizations and do some fun stuff, then we're happy to take suggestions.
Yeah, thank you. That's about it. And this is a bit of an introduction to our great work, and I would like to thank Gats very much for taking upon him the very challenging task of coming up with all these cool ideas for AH64. It wasn't a straightforward port, it was more of a re-engineering of the same ideas for an entirely different platform with different constraints. And I think we now have copious time for questions, so maybe you have any.
Yeah.
Do we have a mic for the questions?
We're using both mics.
Oh.
So if you could repeat the question?
Yes, I will just repeat the questions, that sounds good.
So for a live men compare, are there
The question was, how can we deal with an aligned mem compare if SIMD usage makes it much faster than a string compare, or if we have to resort to the same strategy? The big advantage of a mem compare is that we know where the buffer ends ahead of time. So we don't have to do a null check, and we can confidently plunge into the unknown and just do unaligned reads from the buffer as long as we don't cross past the end of the buffer. So memcomp is much easier than stringcomp because we can just read chunks of the two buffers. One of the two buffers will be unaligned. That's okay. That's a bit of a penalty on some architectures. But these days, the penalty is really low, and you just don't really notice. From you, please.
Does this work for UTF-8 and JSON? Do you care about the characters?
So the question was, does this work for UTF-8 and JSON? Strings can represent JSON. They can also represent UTF-8. So yes, it does work. Separately from this, I've done work with Professor Lemire of University Toulouse on his SIMD UTF library for fast Unicode transcoding. You should check this out. He has also written a library for processing JSON with SIMD techniques, and if you're interested in that, you should also check it out. But that's a different project. It's very cool, but it's not in the scope here. Maybe we'll do something like this in the future. That is the local stuff I've teased. Because local white character stuff is really slow. Everybody hates it. But maybe we can re-engineer the white character handling in FreeBSD to have a fast path for UTF-8 and to then maybe make use of SIMD techniques for faster text processing. We'll have to figure that out. Yeah, other questions? Another one from you, please.
You say you use a trick to read out of bounds, which works great for all platforms, but what about Cherry?
Yes, I'm unfortunately not very familiar with Cherry, but one of the big advantages, so the question was, this whole overrating business, of course, doesn't work with Cherry, where you have capabilities that strictly enforce that you cannot overread array boundaries. But on Cherry, you can just ask the capability for where the array ends. And under the assumption that the array, that the memory management is configured to be conformant with the capabilities. So if a capability tells you that you're allowed to read until this far, then there's actually memory there. Then you can just use this information to avoid crossing into unmapped pages, which might potentially be easier. I do not have any Morello hardware, so I was not able to evaluate this, and I'm actually not really familiar with Cherry in the general case. But it would be interesting to see how this adapts to the capabilities case. Question from you?
What was the motivation for this? Was there a specific application that was particularly slow that this work was done to speed up? Or?
The motivation of this was I was interested in. I started with with Unicode work with Professor Lemire and was looking for other code that would benefit from SIMD optimizations on strings, and I found that libc string functions had some poor performance in the general case, and it would be an interesting thing to optimize. So that's why I proposed this project to the foundation, and they were really interested in the idea, and that's how this whole thing went on. Yeah, a question from you?
How does it work with the compiler built-ins? And are they planned for PC?
How does it? The question was, how does it work with compiler optimizations? Compiler what? Compiler built-ins. If you use a compiler built-in, so the question was, how does this interact with compiler built-ins? And the other one was? And the other question was, are there plans to implement this on PowerPC?
We have discussed that.
Yeah, so for the first part, if you use a compiler built-in, like __ built-in memcopy or something, the compiler will either inline the implementation, in which case our code is not executed, but the compiler authors probably have an idea of what they're doing, or the call is dispatched to a native function. If the call ends up at our libc string functions, our code is used. If not, it is not used. But I think the built-ins actually dispatch to the standard libc functions if the compiler doesn't have any idea what to do with it. As for PowerPC, I would have loved to cover PowerPC, but I unfortunately do not have any recent Power hardware. I do have a PowerMac G5, but it's a bit out of date. Hardware donations welcome. If you give me a Power box, then I will look into it and probably port the code. it would be very interesting, but so far there has not been anyone interested enough to actually donate some hardware and maybe pay for the extra work, because it's really a lot of work to do the board. Yeah, other questions? Yes, please.
In the very beginning, you mentioned that you're not using C to run this, to provide it, and you're using assembly instead of that.
Yeah.
So with this new instruction sets which you mentioned here, how do you plan to move your work onto this new instruction set? Because they have different vector length, right?
Yes, so the question was, if you're writing this in assembly instead of in C, how can you benefit from new instruction set extensions? And the answer is you have to refactor the code, which means mostly it's copy and paste editing, but in some cases you want to leverage new features of the new instruction set, so you have to adapt the code. But it's not super hard, because the newer vector extensions like AVX512 work basically the same way as SSE, just with extra features. So just porting it to AVX512 is mostly an automatic process, where you have to change all the mnemonics to add a V in front, and then change all the registers to turn X into Z, and then change all the data length from 16 to 64 bits and all the increments and so on. There are some slight differences, but they are very easy to work around. So it is not a complete re-engineering of the code, but rather a slight refactor. Some functions particularly benefit, like strcomp, because on AVX512 you have masked reads. So you can actually tell the CPU to only read a given number of bytes into a register. So you can tell it, okay, the string prefix is 7 bytes, so please read 7 bytes from memory. That's allowed, and that would make this a lot simpler. We wouldn't need bounce buffers and so on. Another question from behind? The question was if the unit test suite has been integrated into FreeBSD, and the answer is a resounding yes, it has. Every time I found a bug in the code, I updated the test suite until it was able to find the bug, and all of these changes have been upstreamed as of today.
Another thing we didn't mention was that during my work, I also found a bug in the code that wasn't called by the test suite, which is now patched, and the test suite is
Yes.
updated.
So there was some code review involved in this too. I'm very confident that the code is now bug-free, at least I hope so. Compiling 35,000 packages didn't turn up any more bugs. So if someone finds a bug, I'm very happy, and I hope nobody does. Yeah, we have about 2 minutes left for questions, so maybe someone else has some questions. Another one, please. We haven't really been able to find any really convincing programs where we could tell how much string processing they do. In the past, some FreeBSD contributors just run Perl on some scripts, where Perl does a lot of string processing. But I'm not actually sure of how much libc code Perl uses these days. I think they have switched to their own internal string framework. I'm not really familiar with that, and it's kind of hard to find a benchmark where you can confidently say how much string processing it does. But yes, it would be nice to have some benchmarks. Phoronix did some benchmarks on the current FreeBSD version, and if you've seen these, they have a suspicious performance increase on the text processing bits, which may be related to these changes. But yeah, it would be nice to have some more application-oriented benchmarks. And last one from you?
Have you looked at any architectures which have a load until first fault instruction?
So the question was, have you looked at any architectures that have a load until first fault instruction? This is, for example, the case on ARM SVE, which has an instruction load data into a vector register, and either load the whole register or load until the first page fault would occur. And then don't take the page fault, but instead stop loading and tell the user that you were only able to load that many bytes. And I have prototyped this for SVE and found that it is in many cases slower than working around this problem, because these load until page fault instructions have a non-trivial overhead over ordinary loads. So they may be useful for specific cases, but just using them all over the place is probably not beneficial to performance. So yeah, it kind of requires some engineering and some fiddling around to work around this performance deficiency. But it's a useful tool to have in the toolbox. Thank you. Yeah, and I think the time's now over. Yeah, thank you very much for attending our talk.
Appreciation from